is a periodic function? Oh, we are in 3.1 now. We're talking about periodic functions, which are things that repeat over time. One period of the function is shown in the graph above or below because, again, I stole this from the internet, hence the name of the series. Using this information, find the value of f of 0. Well, this is periodic, which means it does this and then does it again and then does it back here all over the place. So it looks like from 1 to 5, I have this guy, so every 4 spaces it repeats because, 5 minus 1. So what I'm going to do is I'm going to trace this to the best of my ability, which is pretty bad because I'm not good at tracing, although I'll give myself a little bit of credit there. And I'll scooch this over, boop, like so. And so now what I see is I see f of 0. And f of 0 exists right there at -1. So f of 0 is -1. Thanks for watching. F is a periodic function. One period of the graph f is shown below. On the interval -10 to 10, and including those numbers, how many values of x satisfy the equation f of x equals 1? Well, here's issue number 1 and issue number 2. Issue number 1 is I only give you 3 spaces of this thing that's supposed to stretch out between -10 and 10. Issue number 2 is I don't have -10 to 10. So this is how I'm going to handle this. I know that this repeats its behavior every 1, 2, 3 spaces. So what's going to happen is f of x equals 1 exists here and here. And all of these repeat every 3 spaces. So where are we right now? We're at 3 right now for that one. So let's do different colors. Let's ignore the fact that I drew that there. Okay, let's bring back the blue. And so what's going to happen is I'm going to hit this spot every 3 spaces. So 3 plus 3, at 6, this is going to happen again. At 9, that's going to happen again. Now at 12, it's going to happen again, but I don't care. Let's go in reverse. At 0, it's going to happen again. At -3, it's going to happen again. At -6, it's going to happen again. At -9, it's going to happen again. At -12, it's going to happen again, but I don't care about -12. Okay? So also, we are at 1, 2, 3, 4, 4.5 right there at the green spot. So f of x is equal to 1 at around 4.5, which means at 7.5 it'll happen again, which means at 10.5 it will happen again, but I don't care about 10.5. Let's get rid of that comma to keep consistent. Now let's go backwards. At 1.5 it'll happen again. -3 is going to be -1.5, it'll happen again. -4.5, it'll happen again. -7.5, it'll happen again. -10.5, it'll happen again. But that's all that we care about because we're not going beyond -10. So we have 1, 2, 3, 4, 5, 6, 7 instances where this part hits 1, and we have 1, 2, 3, 4, 5, 6 instances where this part hits 1. 7 plus 6 is lucky 13. So kind of a bizarre, unique problem, but the purpose is to demonstrate how periodic functions repeat, and it just makes you think outside the box a little bit. The graph of the periodic function f of x is shown above, or in this case below because I stole this from the internet. Determine the period of f of x. The period is where the process repeats itself. So what you want to do is we see that this is a process that goes up and down, and it repeats itself over time. Now, what we want to do is we want to pick a spot where it's obvious that it repeats itself. And a lot of people might be like, how about 0? Well, if you pick 0, that's great and all, but you don't see an entire completed period when you pick 0. So either pick a peak or a bottom. So I'll pick the peak. And it goes down and above and repeats itself there. Okay? So the easiest way probably to figure out how long this period is you take the largest value, pi over 12, and you subtract the smaller value, so minus negative pi over 4. Okay, I'm not going to be like, let's count how many spaces. That's an option that you can do, but this is something you learned back in Algebra 1 with a number of lines. You just subtract. It's probably easier that way. What I'll do is I'll multiply u by 3 over 3 to make you able to, combine fractions. So this is pi over 12. A double negative becomes a positive 3 pi over 12. That becomes 4 pi over 12 because a pi plus 3 pi is 4 pi's, and 4 pi over 12 simplifies to pi over 3 like so. Periodic functions. The velocity of a particle in meters per second can be modeled by a periodic function v of t for t is greater than 0. Now, okay, so a particle, basically you have this object moving, and this is going to be the velocity. Here is your graph showing that. So you have this weird periodic function, which means it repeats every now and then. A portion of the graph is shown below. Including units, what is the average rate of change of the velocity from t equals 1 to t equals 21? 9 plus 10. So let me see here. These go by normal numbers. So when t is 1, I have what appears to be, oh, this doesn't go by numbers, normal numbers. That's 1. So t of 1 is 1. Terrific. Let's find 21. It's not there. So when you have a periodic function, here's a little trick. I don't want to continue this graph because I'm not a good artist and I don't want to try to draw the grid. That's no good. It looks like what happens is this repeats every 1, 2, 3, 4, 5, 6 spaces, right? We start out by going one flat line, then down, then up, then down, then 2 flat lines. So every 6 spaces, it repeats. In order for you to find out what's going to happen at 21, what you do is you take 6 and you divide that from 21 and find out your remainder. So 6 divided by 21 is 3. 3 times 6 is 18. Your remainder is going to be 3. So t of 21 has the same behavior as t of 3. And at 3, 1, 2, 3, you get 2. Okay, so now we need to set this up. We are being asked to find the average rate of change. The average rate of change is given to us by the formula f of b minus f of a over b minus a. Well, in this case, I don't have f's, I have t's, and I do have f's. I have v's, I believe. There you are. So it's going to be v of 21 minus v of 1 over 21 minus 1. V of 21 we already said is 2. V of 1 we already said is 1 over 21 minus 1 is 20. So to put it all together, because they want us to include the units, we have 2 minus 1. Let me get my calculator. Is 1. We have over 20. And this is the average rate of change, which is something per second, meters per second. So meters per second. Now, some of you might be thinking, you treated t of 21 like t of 3. That's correct. But it still is 21. So we're not going to do 3 minus 1 down here. Very, very, very tricky. We still have to pretend that we're extending all of this time over here. But, you know, that's what we get. 1/20th meters per second. Not very fast this particle is going at that amount of time. But it's average rate of change, not total distance traveled or total, rate. So kind of a bizarre problem. A metronome is a tool aiding musicians in playing rhythms accurately by generating a steady beat. If you've never seen a metronome before, it's the thing that goes like, and everything that it hits that middle part, it ticks and it helps people keep time. Certain metronomes operate using a pendulum that swings back and forth repeatedly, like I just said. Which statement accurately describes the relationship between the beat produced by the metronome and the motion of the pendulum? Both the beat produced by the metronome and the motion of the pendulum exhibit a periodic function with relationship to time. Only the beat, only the motion, neither. Now, what happens is it wants us to talk about the beat, and it wants us to talk about the motion. Okay, so what happens with the beat is every time it hits the middle, it clicks. So it goes. That's periodic because it repeats the exact same amount of time. The motion goes from left, right, left, right, left, right. That is also periodic because it's moving left to right. So both the beat and the motion exhibit periodic relationships over time. That's it.
Which of the following angles share a terminal ray with theta equals 300 degrees? All right, let's take a look at what 300 degrees even looks like. Over here you have 0 degrees. Whenever you're talking about rays in precalculus, you deal with all the way to the right first and you count by going counterclockwise. Every 90 degrees, every quadrant is 90. So, starting here would be 90, 180, 270, and so 300 would be something like that going in that direction. Now, every time I spin completely around, a complete circle is the same as 360 degrees. So if I give you 300, I can literally come up with an infinite amount of other measurements that mean the same thing by adding or subtracting 360. So that's what I'm going to do here. I'm going to take my three options and add or subtract 360 and see if I get 300. So for one, if I add 360, right off the bat, I get 300, like the Spartans. And 1 is my option. If I take 660 and I want to try to make it to 300, what I'm going to do is I'm going to subtract 360, and 660 minus 360 is also 300. So 2 is an option as well. I'm going to do the same thing. We're negative here, so I'm going to add 360, and by adding 360, I am at negative 40, so I'm not in the area that I want to be at. If I add 360 again, which means I spin around again, I end up with 320. So close, but only 1 and 2 are going to be correct because only those guys are the same as that. The end. An angle with a measure of 5.7 pi would be equivalent to which of the following angle measurements? Well, if I'm given something in radians and I'm talking about an angle, what I do know is if I have a coordinate plane and I were to try to measure an angle, I would start over here at 0 and spin my way around. Now, every time I spin around in this direction, I complete a complete circle, which is the same as 2 pi. So what I need to do is I need to take that 5.7 pi and either add or subtract 2 pi until I hit one of these guys to see which one of these guys is the same. And if you're wondering, oh, well, hold on, isn't 5.7 pi and like 3.7 pi different? No, if I were to take 5.7 pi, which looks something like this, right, give or take. If I were to take 5.7 pi and subtract 2 pi from it, I get the same thing because I'm circling 2 pi. So I'm going to take that, and all of these numbers are smaller. I'm going to take 5.7 pi and subtract 2 pi until I get one of these guys here. So if I take 2 pi away from that, I get 3.7 pi. Okay? None of those. If I take 2 pi from that, I get 1.7 pi. So I passed u, so none of those. If I subtract 2 pi from this, I get negative 0.3 pi. So that one. But if I just want to be safe and stuff like that, I could take subtract another one and get negative 2.3 pi, which passes u, and do it again, which passes u. So there you go. There you have it. You're allowed to take anything and add or subtract 2 pi, and it'll end up being the same exact angle measurement. Fun stuff. The measurement of an angle in standard position is listed. In which quadrant is the terminal ray? Now, a terminal ray is basically, if you were to look at it something, and these are in radians, terminal rays exist at its like original measurement between 0 and 2 pi. Okay, if I were to measure an angle, you always start out at the right with 0 radians. Every time we spin around a complete circle, it's the same as 2 pi, which means half a spin is 1 pi, a quarter of a spin is pi over 4, 2, just kidding, pi over 2, and 3/4 of a spin is 3 pi over 2, or 1.5 pi. Squeeze that in there. Now, what I need to do with these guys is I need to subtract or add 2 pi, because every spin is 2 pi and it lands you in the same exact spot. I need to add or subtract 2 pi until I land in the sweet spot between 0 and 2 pi. And when I do, I'll figure out if we're in quadrant 1, quadrant 2, quadrant 3, and quadrant IV, also known as 4. Like and subscribe if you enjoy that joke. You won't. Let's subtract 2 pi. That gets me 0.9 pi. 0.9 pi is less than 1 pi, but greater than half a pi. So we're looking at quadrant 2 for this guy right here, quadrant 2. With this, I'm going to be adding 2 pi a bunch of times. So if I add 2 pi, that gets me here. If I do it again, that gets me here. And if I do it again, that gets me here. And if I do it again, that gets me here. Adding 2 pi one more time will get me 1.9 pi. 1.9 pi is less than 2, but greater than 1.5 pi, which lands me in quadrant 4. Thanks for watching. The sector in the figure has a central angle with a radian measure of pi over 3 radians. The arc length of the arc AB is 6 pi. What is the radius of a sector? So this is how I like to view this. You may have learned in, geometry, a little formula for arc length and stuff like that, but I kind of like to view this as the whole thing being the circumference. Circumference of a circle is pi, or 2 pi r. I almost said pi r squared. That's the area. Silly me. Now, the arc length is if I were to take just a chunk of my circumference. Now, how do I figure out what that chunk is? I'll call this AL for arc length. You're going to take 1 2/5 of your chunk to find out what the arc length is. So I'm going to say theta over 2 pi times 2 pi r. Now, what this does here is the 2 pi and the 2 pi cancel out. So the arc length is just going to be whatever my theta is times whatever my r is. Okay, I don't know what my r is. That's what I'm trying to find. But I do know that my arc length is 6 pi. I know that my theta is pi over 3, and my job is to find r. Multiply both sides by 3 over pi, like so. Multiply both sides by 3 over pi, like so. The pi's cancel out, and 3 times 6 is going to be 18, so my radius is going to be 18 units long. Strange problem. I've seen worse, though. A line is drawn from 0, 0 to the point shown to create an angle A with the positive x-axis. All right, so here's the positive x-axis. I'm going to try to draw a line from there to there, and I had it, and then I blew it, but if I just, make it a nice thick outline, you'll never know that I screwed it up so badly. Okay, so there's my line. Boom. It's called angle A. Boom. Write a ratio for sine A, cos A, and tangent A. Basically, what we're looking at is we're looking at some geometry SOHCAHTOA stuff, but we're trying to get rid of the concept of SOHCAHTOA. SOHCAHTOA, of course, gives you those trig ratios with opposites and adjacents and hypotenuses, if that's even a word, yada, yada, yada. But let's not memorize that for pre-calc. Now that we're in AP Precalculus, let's try to memorize these instead. Sine of theta, or in this case A, is going to be my y value over my radius. Okay. Sine of, let me get a different color, sine, or rather cosine of A is going to be my x value over my radius, and tangent of A is going to be my y over x. Now, where are these y's and x's coming from? Well, if I were to look at just sine and think of SOHCAHTOA thoughts, SO stands for opposite over hypotenuse. My opposite side is basically how high I go to hit my y value. My hypotenuse is how long my radius is. So this is what I want to memorize for AP Precalculus. Get rid of SOHCAHTOA. All that stuff that your geometry teacher back in the day, ignore it. It's gone. It's dead. Now, what do I know? I know my x value is 1.95. I know my y value is 2.9. Is my r 1? No. My r appears to be 3.5. My r appears to be 3.5. So sine A in this case is going to be my y value, 2.9, over my radius, 3.5, and we'll leave it like that. Cos A is going to be my x value, which is 1.95, over my radius value, which is 3.5. And tangent is going to be my y value, which is 2.9, over my x value, which is 1.95. So you will see this a lot. I'm going to make a lot of videos that look very, very, very similar to this. Watch and like them all. Please, I beg you. Please, I need the money. Write a ratio for sine alpha. All right, sine in precalculus is given to you, rather than thinking SOHCAHTOA thoughts, which you're still allowed to do, I'm going to think this instead, y over r. Y stands for the y value, and r stands for the radius, which appears to be 1. So I'll do that right there. Sine alpha, right here, is going to be literally the y value over the radius, which is 1. So sine alpha is my y, 0.6 over 1, which simplifies nicely to sine alpha equals 0.6. Bada bing! Consider point P on the unit circle with coordinates x, y in quadrant 2. Which of the following values are equivalent to y? All right, so sine, more sine, and even more sine. There's a point, there's a unit circle. Now that we're in AP Precalculus, get rid of SOHCAHTOA thoughts and replace them with this. Sine theta, okay, in general, and yeah, this does come from SOHCAHTOA, but we're simplifying it, is going to be y over r. Now, the nice thing about sine theta with a unit circle is r is 1. So sine theta is going to be y over 1, which is just y. So number 1 is going to be very basic. Now let's be careful before we move forward. We're looking at this point right here. This point lives in quadrant 2, which means this point has a value of negative like 0.3, positive like 0.9. But we'll just focus on the fact that it's negative x, positive y. So issue number 1, sine theta is going to be just a positive y value. So sine theta is y for issue number 1. Circle that guy. Now let's take a look at concern number 2. Sine 180 minus theta. 180 is a half spin around the circle. So 180 minus theta has me taking this point and spinning it over here somewhere, give or take. This point is now a positive x, negative y. So issue number 2, sine theta is going to be a negative y value, which means 2 is no good because we want just a regular y. Now 3, I'm not going to overthink it at all. 3, that's supposed to be purple, is 360 minus theta. Basically, if you're going to go 360, you're going to spin it completely around and end up in the same exact spot that you were before. So 3 is the same as 1. So 3 is an answer because 3 is the same as 1. Thanks for watching. Hope this helps. Consider the point P on the unit circle with coordinates x, y in quadrant 2. Which of the following values are equivalent to x? So it gives me a bunch of cosines, fun stuff, and it gives me a point, unit circle, makes life a lot easier. Let's explain what cosine is before we do too much. Now get rid of SOHCAHTOA thoughts and have this memorized instead. Cos theta is going to be x over r. X being the x coordinate, r being the radius of your unit circle. Now, since this is a unit circle, we can assume that r is 1. So cos theta is x over 1, or just x. Now, here's the point that we're focusing on. I don't know exactly what this point is, but what I see is this point lives in quadrant 2, which means whatever value x is, it's a negative x. And whatever value y is, it's a positive y. So this could be like the point negative 0.3, positive 0.9, or something like that. So let's take a look at issue number 1. Issue number 1 wants cos theta. Well, in this case, cos theta is going to be my x value. My x value is negative, so cos theta is negative x. They want regular x, so 1 is not an option. Option number 2 is they want me to do 180 minus theta. 180 minus theta says, well, here's my theta, subtract it from 180. 180 is a half spin around the circle. So if I take that point and spin it halfway around the circle, I'm now over here. Now this is quadrant 4, where x is positive and y is negative. So cos 180 minus theta, cos 180 minus theta is going to be whatever my x value is. My x value in this case is positive, which means 2 will work in this case. Now 3, let's not overthink it. 3 is pretty easy. 3 is asking 360 minus theta. Well, here's my original point. If I spin this or subtract this from 360, I'm literally taking it and moving it one full circle, which means I land on this original point. So 3 is 1. And if 1 is no good, then 3 is no good, which means 2 is my only option that will make sense. The end. Consider the circle centered at the origin with points A, B, C, and D on the circle. Angle theta in standard position has a terminal ray that intersects the circle at a point. Which point of intersection, point, redundant, would result in the greatest value for tangent theta? All right, so what's tangent theta in AP Precalculus land? Well, tangent theta is going to be the same as y over x. So this is what I need to do. I need the greatest possible value. I have A, B, C, and D living on this unit circle with a radius of 5. Not that the radius matters too much, but it kind of does help. It helps me visualize things a little bit better. But what I need to do is I know that A and B live in quadrant 2. A and B both have negative x values as points and positive y values as points. C and D both have negative x values as points and negative y values as points. So this is what I'm going to do. I'm going to kind of predict A, B, C, and D based off of where they live and find out which 2 of these could possibly be my answer. Once I eliminate 2 answers that definitely won't work, I can move on to the second part. So part 1 is me saying here's A, here's B, here's C, and here's D, and finding out which 2 of these could possibly be greater. Now, tan theta is y over x, which means A is going to be y over negative x. B is also going to be y over negative x. C is going to be negative y over negative x, and D is going to be negative y over negative x. Now, what this does for me, is I could do a little bit of simplifying and remind myself that, oh yeah, negative y over negative x is the same as positive y over positive x, and same thing for you. So of my four possible options, you're negative, you're negative, you're positive, you're positive. Neither of you can possibly be greater. So now I need to focus on C and D. Now let's just make believe that you have no clue what these points are. This is what I do know. I know in this case my radius is 5. So C could possibly be the point like, I don't know, like -4, -3. Because this stretches out to x more than it does to y. This has a smaller x value but a larger y value. So let's swap them. Smaller x value, larger y value. Let's say that you're -3, -4. And by smaller, I mean the digit attached to x. I know the negatives kind of flip-flop things, but let's just make believe that those are my two options. That would make C -3 over -4, which becomes 3 over 4. That would make D -4 over -3, which is 4 over 3. So in this case, when the y value, or when it's, I guess it's closer to the y-axis, my number is going to be getting larger. My tangent theta is going to be getting larger. So in a case like this, where I have a unit circle with a radius of 5, my answer is going to be D. So very strange problem. Made me think outside the box a little bit. Maybe think outside the circle. Like and subscribe, please. An angle alpha corresponds to a point on the unit circle √3 over 2, 1/2. What are the values of sine alpha and cos alpha? All right, well, we have this point right here. Let's label U, X, and Y. If this is the unit circle, we can assume that the radius is 1. Okay, so in precalculus, we refer to sine alpha, no longer thinking SOHCAHTOA thoughts. We just know that this is going to be y over r. So in this case, using this point right here and the fact that r is 1, sine alpha is going to be 1/2 over 1, which means sine alpha is just going to be 1/2. Cos alpha is going to be x over r. So in this case, x is √3 over 2. R is 1. So cos alpha is just √3 over 2. Okay? Very basic stuff. Just remember, sine alpha is y over r, cos alpha is x over r, and if you needed it, tan alpha would be y over x, but we don't need tan alpha. Just those guys. Thanks for watching. An angle in standard position measures 270 degrees. The terminal ray of the angle intersects a circle centered at the origin with radius 3 at point Z. What are the coordinates of point Z? Time to show off my drawing skills, which are bad. That's a circle. This is a coordinate plane perfectly going through the circle like so. When you measure out an angle, you start out here on the positive x-axis and you work your way around counterclockwise. If we're dealing with degrees, you would be 90 degrees, you would be 180 degrees, you would be 270 degrees, and 0, 360 repeats itself, yada, yada, yada. I need to get to 230. So here's my circle. I'm going to go around counterclockwise from 0 to 90 to 180 to 270 and put a dot right there. Now, the radius of this circle is 3. We're calling that dot Z, and they want to know what Z is. Well, Z is the point on the coordinate plane on the y-axis, 0, -3. So pretty basic problem, pretty simple. And that's all we had to do right there. The sine of an angle in standard position is 1/2, and the cosine of this angle is negative √3/2. At which point does the terminal ray of the angle intersect with the unit circle? Now that's very important that it mentions unit circle because that means the radius is 1. Why do I care about that? Well, it talks about sine and it talks about cosine. And in AP Precalculus, when we talk about the sine of an angle, which I don't have, so I'll just call it theta, sine of theta is going to be the y coordinate over r. Also, and I'll write this out and get it out of the way, the cosine is going to be x over r, like so. Now, why is that important? Well, sine theta is 1/2. Now, if r is 1, then that just means sine theta is y, because it's y over 1. And sine theta is also 1/2, which tells me that y is 1/2. Similarly, cos theta is x over r. Since r is 1, cos theta is x. Cos theta is also negative √3/2. They want us to take this information and come over here and select the letter that seems to match this information. Well, this information gets me an x value and a y value, which means it's going to be a point. And that point is negative √3/2, positive 1/2. And a point in the form of negative, positive is going to live in quadrant 2, which means K has got to be my guy. All right? So there you have it. Weird problem. So much fun, though. All right, let's complete this unit circle. This is not the only unit circle video that I have, so I highly suggest that you watch both of them just for fun. Now, let's start out the unit circle by labeling my degrees. Now, we always deal with radians here in pre-calculus land, so we always start out at the positive x value, the positive x-axis at 0 radians, and then up here you have pi over 2 because halfway through it is going to be pi, so I'll put that there, which makes you 1.5 pi, also known as 3 pi over 2, like so. Okay, this is going to be 1/3 of my way through, 1/2 of my way through, and 2/3 of my way through. So 1/3 of pi over 2 is going to be pi over 6. 1/2 of pi over 2 is going to be pi over 4. And 2/3 of pi over 2 is going to be pi over 3, because it would be 2/6 pi, or yeah, 2 pi over 6. Okay, coming over here now, I'm going to add 1/3, so that's 2 pi over 3. This is halfway between pi over 2 and pi, so that's 3/4 of a pi. And then you're 2/3 of my way through, so you're going to be 5 pi over 6. Okay, and now this part is just a matter of you taking all of these values and adding a pi to it, or, you know, whatever over whatever. So like 6 pi over 6 plus pi, you know, plus pi over 6 is going to be 7 pi over 6. Okay, this is going to be 5 pi over 4 because you're going to add 4 over 4. This is going to be 4 pi over 3 because you're going to add 1 to that. And then this is going to end up being the same idea. You're just going to add 1 to that. So that's going to be 5 pi over 3, like that. This is going to be 1 plus that, so 7 pi over 4. And last but not least, we're going to add 1 to that, so 11 pi over 6. Okay? All right. This is a unit circle. So you are, let me get different colors now that I have all my pi's written out. You are going to be the 0.10. You are going to be the 0.01. You are going to be the point negative 10. And you are going to be the 0.0 negative 1. Now, the trick behind filling out the unit circle is you kind of want to imagine everything as root something over 2. Okay? Root something over 2. Now, when I work my way around, okay, you're going to start out with root 3 over 2. Root 2 over 2. And root 1 over 2. The square root of 1 is 1, so you can just do 1 over 2. Now, working my way backwards is literally working my way backwards. You are now root 3 over 2. You are root 2 over 2. And you are root 1 over 2, which is just 1 over 2. This is quadrant 1, so the points are given to you as a positive value and a positive value. Leave it like that. Now, as you keep going, this point lines up with that point over there. But I know that this is quadrant 2, which means the x values are going to be negative, but the y values remain the same. So you are 1/2, negative 1/2. Let me make that more obvious. Negative 1/2 root 3 over 2. You are going to be negative root 2 over 2, regular root 2 over 2. You are going to be negative root 3 over 2, 1/2. Okay? As I come down here to quadrant 3, you guys seem to line up very, 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 very nicely. However, this is quadrant 3, which means everything is negative, 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 negative. Okay, and you're just going to follow the same procedure as I do over here. So you are negative root 3 over 2, 1/2. Root 2 over 2, root 2 over 2, both negatives, and you're going to be the same as that, negative 1/2 and negative root 3 over 2. Last but not least, we're going to continue the process. This is quadrant 4, which means you're going to have a positive value and then a negative y, positive value, then a negative y, positive value, and then a negative y. And these guys seem to line up nicely. So I'll call you positive 1/2, negative root 3 over 2. I'll call you positive root 2 over 2, negative root 2 over 2. And I'll call you positive root 3 over 2, negative 1/2. Okay? So basically, I mean, I don't know. It is what it is. Unit circle is never the prettiest thing in the world, but once you kind of figure out the starting point, the rest of it just falls into place nicely. So you don't have to go crazy trying to memorize too much. But there it is, unit circle. An angle alpha is in standard position and measures 3 pi over 4 radians. What are the values of sine alpha and cos alpha? All right, so I'm going to draw myself a unit circle, which I'm awful at, but I'll do the best that I can. Okay. Maybe I can take that and just scooch it over there. Oh, look at that. Perfect. Perfect. All is well. All right. 3 pi over 4. Where is that? Well, you're 0. You're half a pi, and you're a full pi. So 3/4 of a pi, I don't know why I put that over there. Let's get rid of you. 3/4 of a pi is halfway in between pi over 2 and pi. Now, when we look at a unit circle, we always have our axes, but we also have 3 dots on each quadrant. So you have, the 1 stuff and the 3 stuff, but the halfway through is super nice because when it's halfway through, your values are going to be root 2 over 2 and root 2 over 2. Now, before you scream at me and run to the comments and be like, you forgot something, this is quadrant 2, which means my x value is going to be negative. So my x value is going to be negative, my y value is going to be positive. This is unit circle, so my r is going to be 1. They want sine alpha and cos alpha. So sine alpha in precalculus land is going to be y over r. In this case, r is 1. My y value is root 2 over 2, which means my sine alpha is just going to be root 2 over 2, because when you divide it by 1, nothing changes. Similarly, cos alpha is going to be my x over r. My r is 1. My x is negative root 2 over 2, and negative root 2 over 2 over 1 is negative root 2 over 2. So that's how you would do these guys without the use of a calculator. This is it written in perfect form. Fun stuff. For angle theta in its standard form, it measures 4 pi over 3 radians. What are the values of sine theta and cos theta? Well, let's draw ourselves a unit circle, which I'm terrible at. See? Let me try to draw a circle. I can, always move things around when they end up looking like that. So there it is. They want 4 pi over 3, which is more than pi. Pi lives right here. 4 pi over 3 is going to live in the sweet spot between pi and 3 pi over 2. Now remember, in each quadrant, I have 3 main points that I look at. Okay? 1/3 after pi would be 7 pi over 6, not u. A halfway through between pi and 3 pi over 2 would be 5 pi over 4, so not u. And 2/3 plus pi, 2/3 of my way through, which is going to be 1/3 of pi, is going to be 4 pi over 3. So you are my third dot right here. Okay, so I'm looking at you, this point right there. Now, whenever we label our unit circle, okay, we're always thinking that square root of whatever number over 2. Okay, my x values starting from the x-axis, whether I'm moving up or moving down, my x values are going to start out with that number 3. So u would be, square root of 3 over 2. U would be square root of 2 over 2. But my third point, which is the most important point, would be square root of 1 over 2, which is 1 over 2. Okay, similarly, if my x value starts with 3, my y value starts with 1, so you would be 1 over 2, root 2 over 2, and you would be root 3 over 2. Now, before you start screaming at me, I know I'm not done yet. This is quadrant 3, which means my x value is negative and my y value is also negative. So this is the point that I'm mainly going to be dealing with, negative 1/2 and negative root 3 over 2. So I will label you x and I will label you y. Now this is a unit circle, and what's very important about the unit circle is r equals 1. So when I'm trying to find sine theta and cos theta, I know that sine theta in precalculus land is going to be y over r, and I know cos theta is going to be x over r, like so. My y value in this case is negative root 3 over 2. Negative root 3 over 2. My r is 1. So sine theta in this case is going to be negative root 3 over 2 divided by 1, which is negative root 3 divided by 2. My cos theta is going to be my x value over r. My x value is -1/2, and my r is 1 again. So -1/2 divided by 1 is -1/2. So there you go. Fun stuff. Tons of fun. The figure shows a circle of radius 4 along with 5 labeled points. You got A, B, C, D, and O. The measure of angle DOC is 2 pi over 3. So let's quick label that. 2 pi over 3. So I'll put the 2 pi over 3 right there. A familiar number if you remember your unit circle. The measure of angle AOB, which is U, is half of AOC. One of my favorite people. What are the coordinate points of point B? Okay, so first things first, before I label more of my unit circle, kind of unit circle thing, let me make clear that I'm dealing with points here. Okay, now normally when I think, when I see all these sines and cosines and stuff like that, and I see unit circle stuff, I think, all right, well, sine of theta, or whatever you want to call it, is y over r. R is not 1 in this case. And also, I want to turn this into a point. So what I'm going to do is I'm going to multiply both sides by r, and I get r sine theta equals y. And you might be thinking, well, how will that help us? I'll show you in a minute, because over here I can similarly write out that cos theta equals x over r. Multiplying both sides by r there gives me r cos theta equals x. So now I can organize this in a point form as r cos theta, r sine theta. All right, I care about b, which is going to be 1/2 of AOC. So if I know what 2 pi over 3 is. 2 pi over 3 is 1/3 of my way after this y-axis. That's 1/3. So this remaining part is going to be 2/3 of the entire quadrant. And so half of 2/3 is 1/3. So B represents the 5 pi over 6 value. 5 pi over 6 value is what B represents. And that's what I'm trying to find. I'm trying to find the coordinates of B. So I know that R is my radius. So when I write this out, R is my radius, and my radius is 4. So let me write that out. My radius is 4. Okay, if this is 5 pi over 6, according to the unit circle, that gives me the point. And remember, the way you handle this is you always think the cube or the square root over 2. And when you start from the y-axis, the x value starts at 3. So the b value is going to be -√3 over 2. And it's negative because it's quadrant 2, and that's a negative x value. The y value is going to be positive because in quadrant 2, the y value is positive. And this works your way up from 1/2. All right, so r cos theta is going to be 4 cos 5 pi over 6. So I guess I really didn't need the point there, unless I needed to simplify further, but I guess they don't want me to do that at all. The y value is r, which is 4 sine theta, which is 5 pi over 6. Now, if you're worried about negatives and stuff like that, don't worry about negatives and stuff like that, because the negatives will follow through when you plug things in. Okay, so if you're thinking that the answer should be A, it's not going to be A, it's going to be B. Now, if I were asked to take it one step further and actually solve for this, then I would use these numbers, and yes, I would get negatives, but again, I'm not doing that. I'm just writing out 4 cos theta, which means 4 cos 5 pi over 6. So kind of a strange problem, not a big fan of it, but yeah, that's how you do it. Fun stuff. The figure shows a circle of radius 6 along with the origin and 3 labeled points on the xy plane. If the coordinate of x are 3 and -3 root 3, what is the measurement of angle AOX? So, okay, if we're dealing with coordinates and you're dealing with a non-unit circle, which means the radius is in this case 6, you're going to view it like this. In a previous video, I kind of broke things down where I reminded you that sine theta, or whatever it is that we're talking about, is y over r, right? And if I multiply both sides by r, I now get r sine theta equals y. Similarly, cos theta is x over r. And if I multiply both sides by r, I now have r cos theta equals x. Why does that help us? Well, now I have a y value, now I have an x value, and I can write these guys out as points. So my x is going to be r cos theta, r sine theta. That's my point. It gives me the coordinates. So the coordinates are actually going to be 3 equals r cos theta. And by the way, theta is going to give me the angle measurement of, not AOX, it's going to be giving me the angle of BOX, so I have to be super careful with that. Super careful with that. But anyway, not there yet. 3 equals r cos theta. So maybe I could just deal with that. I know that r is 6. So 3 is going to equal 6 cos theta. Dividing both sides by 6 says cos theta equals 3 over 6, which is a half. Now, since I'm looking at this point down here, I remember that cos theta has to do with the x value. Okay, when I move from the x-axis and I do the whole square root over 2 stuff, okay, I know I'm going to have 3 dots, right? I'm going to have 3 dots, and the first dot is going to be root 3 over 2 for my x value, then root 2 over 2, and then 1/2. So this x value is going to be this dot right here. This dot has to do with the radian measure 5 pi over 3. Now this 5 pi over 3 considers the whole thing. I don't want the whole thing. I want AOX. So rather than do the whole thing, I'm going to subtract out a pi from this. So minus a pi is 5 pi over, so basically just subtract 3 over 3, and you get 2 pi over 3. So a very, very, very bizarre problem, very potentially confusing, but, you know, these aren't supposed to be easy. They're just supposed to be fun, and it was. Angles A and B are in standard position on the xy plane. The measure of angle A is pi over 6 radians, and the measure of angle B is 11 pi over 6 radians. I know where these points are. Let's draw ourselves a unit circle, the best that I can, the best that I can. Pi over 6 lives right here. Okay, now remember, every quadrant has those 3 dots. 11 pi over 6 is right underneath it. If you don't have the unit circle familiarize with it, because otherwise you're going to be like, huh? Now my job, the terminal ray of both angles intersect a circle centered at the origin with radius 16. All right, so you are going to be 16. You are going to be 16. What is the distance between these 2 points of intersection? Okay, all right, so I need U and U. So basically, I care about the y value and the y value. So let's go back, and I've done several problems like this. I need to deal with the sine cosine function that deals with the y. Well, the one that deals with the y is sine. So you may remember that sine theta is x over, or y over r, y over r, y over r. Okay. Now, if I'm looking at it this way, and I have a radius that is not 1, I should probably multiply both sides by r. So r sine theta equals y. Now, my y value is basically going to be r, which is 16, sine theta, which is 11 over 6. Now, that gives me my y value. Okay. Now, on top of that, this y value is the same exact thing as that y value. But they don't want me to set it up like that. What they want me to do is this is going to give me, if I were to type out 16 sine 11 pi over 6 equals y. If I were to do that, it's going to give me a negative y value, because what it's doing is it's giving me a point in quadrant 4. I don't want a point, I want a distance. So when I figure this out, I want my positive y coordinate, whatever that is, minus that y coordinate, because that y coordinate is going to be negative. And so it's going to be essentially a y minus a minus, which is a plus. So I want 16 sine pi over 6 minus 16 sine 11 pi over 6. Because if I were to type that into a calculator, it would give me a negative y value, and minus a negative makes a positive, which gives me the full length there. And by doing that, I have a. So kind of a weird problem, very weird problem, but that's how you do it. All right, we are now in section 3.4, and with 3.4, we are given an idea of what the graphs of sine and cosine look like. So when we go into this weird, strange problem that might look like something from 3.3 or 3.2, we now know what cosine looks like. So we are given this angle theta in standard positions shown in the figure. The function g is given by just regular cosine a. For the angle A, which is not shown, A is going to be in between this theta and 3 pi over 2. Okay, so let's graph what cosine kind of looks like. All right, by the way, we only care about up until 3 pi over 2, but let's just graph the first period of cosine, which looks like this. Cosine starts up at 1, okay? At half a pi, it hits 0. At pi, it bottoms out at -1. At 3/2 pi, it hits 0 again and then comes back up and repeats at 2 pi. So let me attempt to draw this out. This never goes well. This never goes well at all. I'm singing you a song. Not bad. All right. So that's what cosine looks like for its first period, and then it repeats. I care about 3 pi over 2, which is this guy right there. All right, so what we know is alpha is going to be larger than theta. It looks to me that theta is somewhere larger than pi over 2. All right, so somewhere. So theta is going to be somewhere in this range, okay, give or take. Okay, so that's theta. Whatever alpha is, alpha's got to be bigger than that, okay? So any of this area right here. Alpha or A, I think I keep calling it A. It might be alpha, I don't know. I'm just thinking of manliness right now, so I keep saying alpha. Basically, what's going to happen is no matter what, since theta appears to be bigger than pi over 2, what's going to happen is alpha, no matter what, is going to be underneath this x-axis, right? I mean, that's what it appears. It's basically saying, I'm going to give you an alpha. I'm going to give you a theta. Theta
at its smallest is going to be some negative number. Alpha is going to be negative no matter what. So it's safe to say that like alpha could live here, in which case it's bigger than theta. If theta was, alpha could live here, at which case it could be smaller than theta. The question is asking you, like, what's the graph, or what happens if you plug in alpha? What happens if you plug in theta? Is no matter what you plug in alpha, no matter what, you get a smaller value than when you plug in theta? Maybe. Is no matter what, if you plug in alpha, you get the same thing? Maybe. I mean, if theta was this point right here, I could choose an alpha that's the same. If theta was this point here, I could choose an alpha that's larger. And if theta was a point here, I could choose an alpha that's smaller. So this is just a really strange problem where I'm using a very unique situation, again, stolen from the internet, where I need to focus on what the graph of cosine looks like and what that could mean for some random alpha and random theta. So I don't know. I don't like it. This is a stupid problem. But, like and subscribe anyway because you love me and I love you. For the function f of theta equals cos theta, what are all values of the domain when f of theta equals 1? All right, so let's take a look at what cos theta looks like. We're now in section 3-4, so we know what sine and cosine look like from a graphical standpoint. So cosine starts up here at 1, bottoms out at -1. Okay, starts out here, it crosses at half a pi, it bottoms out at pi, at 1.5 pi, it comes back up, and it peaks out at 2 pi. Okay, so those are the sweet spots. Starts up here, bottoms out there, hits the x-axis, peaks out at 2 pi, repeat. Now, I care when f of theta equals 1. Now, 1's right here. F of theta is going to equal 1 an infinite amount of times because it always peaks out at 1. Look at that perfectly straight line to represent that. So basically at 0, it's 1. And at 2 pi, and then at 4 pi, and then at 6 pi. So how do I represent that? Okay, well, this is going to happen every 2 pi's. Well, what I'll say is this is going to equal 1 when theta equals 2k basketball, 2k pi. Now, what is k? K is all integers. Any integer for all k is you know what? Let me not use calculus language. I was going to say I was going to use the integer thing for all integers. K. So if k is 1, 2 pi makes sense. If k is 0, 0 makes sense. If k is -1, that makes sense because it's -2 pi. So any integer k, theta, is going to be a possible answer because it's periodic and it repeats itself. So there you go. Given a circle with radius 1 centered at the origin, unit circle, there is a point M where the terminal ray of the standard position angle theta intersects the circle. The coordinates of point M are a half, √3,2. What is the sine of angle theta? So, okay, this is pretty not so bad. This is just unit circle stuff. Even though it's section 3-4, it's still unit circle stuff because of the fact that the radius is 1. We have a point M at 1/2 √3/2. Okay, so if you remember your unit circle, there's 3 dots. Okay, 1/2 √3/2 is going to live at this dot up here. Okay, the dot closest to the y-axis. What is the sine of angle theta? I don't even have to go that far. Basically, sine is y over r. Sine theta is y over r. r is 1, and y is root 3 over 2. So the sine of angle theta is just root 3 over 2. I feel that's a bit too easy, but that's the problem. So I don't know. Yeah, hopefully you see a gentle problem like that on a future test or something. Hope it helps. All right, we have a really strange one here that seems like it should be easy, but it's not. So let's take a look at it. An angle measuring 2 pi over 3 radians is in standard position and intersects the unit circle at point S. Okay, so we're talking unit circle thoughts. So I'm going to draw a unit circle, not super necessary because of how strange this problem is. Look, it's absolutely perfect. No flaws here whatsoever. It gives us sine of our angle equals -1/2, and it also gives us cosine of our angle equals root 3 over 2. What is the y coordinate of point S? Now, when we're dealing with unit circle, we can use the fact that our x value is cos theta, our y value is sine theta, right? It wants the y coordinate of this point, which means it wants this guy right here. And it tells us what this guy is. It tells us that it's -1/2, which, just for funsies, would also mean that the x value is root 3 over 2. So this is our answer. We're done. But I want to kind of analyze this because I did this problem, I looked at it, and I approached it the wrong way. And then, of course, I deleted it. And you're never going to see that because, no man here makes mistakes, even though I do it all the time. My commenters remind me. This point lives right here. And you're like, hold on, time out. Wait a minute. If the angle measures 2 pi over 3 radians, this is pi. 2 pi over 3 is less than pi. Shouldn't our point be up here? Yes, if you're going in the positive way. When you're dealing with an angle in standard position, angles in standard positions always start out with the positive x-axis. However, it's allowed to go this way if they don't tell you that that's the way it's going. So kind of a tricky problem. Not a big fan of it because initially when I did this, I went this way and I figured out that my dot should be up here, but it doesn't say that it has to go in the positive direction. So it tricked me, and I don't like being tricked. I don't like being fooled. Consider the function f of x equals sine x. Determine where the graph of f of x is concave up. This is section 3.4, so we are to assume that we know how to graph sine x. So let's graph sine x and see what we come up with. Sine x starts out at the origin, 0, 0. Goes up to 1, bottoms out at -1. Okay, peaks out at 1/2 pi, hits the x-axis again at regular pi, bottoms out at 3 over 2 pi, and then comes back up to repeat the process at 2 pi. Repeat, repeat, repeat. So let's draw that out, which I'm always really bad at. Yep, see how bad I am? Michael Jackson sang a song about that. So in a perfect world, it would look like this. Now, concave up looks like that. So where does this guy look like that? Well, between pi, but not including, and 2 pi and not including, which means B is where it's concave up. Thanks for watching. Consider the function g of x equals cos x. Determine where the rate of change of g of x is decreasing. Now, this is 3.4, so this is assuming we know what cos x looks like. So let's draw cos x out. Cos starts at 0, 1, and eventually will bottom out at -1. It starts up here at 1/2 pi, hits the x-axis, bottoms out at regular pi, comes back up at 1.5 pi, and then peaks completely out at 2 pi. So let me draw that out, probably poorly because that seems to always happen. So there it is. That's part 1. Here's part 2.
here's part 3, here's part 4. Now, my job is to find out where the rate of change is decreasing. What does the rate of change is decreasing mean? That means concave down. Okay, rate of change is a fancy word for slope. And this slope, as this moves to the right, gets smaller and smaller and smaller and smaller. So concave down is another way of saying rate of change is decreasing. So where is this guy concave down? Where it's concave down in two areas. Here, that's one side of concave down, and here is the other side of concave down. So we have two answers here. Between 0 and pi over 2 is concave down, and between 3 pi over 2 and 2 pi is also concave down. So we will select A for this one, and we'll select D for this one because those are both my possible answers. Which of the following are sinusoidal functions? Now, this is 3.5, and you were probably taught that a sinusoidal function is something in this form. Y equals A, which A is the amplitude, sine times B, which is the frequency. If you haven't learned frequency, you will. Minus C, which is a phase shift, plus D, which is a vertical shift. Okay, so basically, if you can write it out like this, it's a sinusoidal function. Now, if you look at 1, 2 sine theta is just that, where A is 2, and B and C or D, they don't really matter. So 1 is an option. What you don't see is sine being in the denominator. Okay, this will not give you a regular old sinusoidal function that looks like this. So not 2. 3 technically is because cosine is sinusoidal. And basically 4 here is the same thing as 1. It's just you can write this out as 1/2 sine theta. So everything here except for 2 is good to go for sinusoidal functions. What is the frequency of g of theta equals cos theta? Well, whenever you have a sinusoidal function, the number in front of theta, in front of your angle, is technically considered the frequency. So the frequency is 1. Thanks for watching. Identify the true statement or statements about the amplitude of f of theta equals sine theta. Now, this is sine theta very, 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 very quickly. There's no attachments. There's nothing being multiplied to it, no phase shifts, nothing like that. This is an invisible 1 sine theta. So sine looks like this, where it repeats, just like, what's her face, Selena Gomez once said. Now, the amplitude is not from the tippy top to the very bottom. The amplitude is the measure from the tippy top to the midway line, or the midline as some people call it. So how do I describe that here? The amplitude is the distance from the origin to a maximum point. Well, no, that wouldn't work here for sine because that looks like it would have to be some kind of Pythagorean theorem triangle looking problem, and that's technically not true, at least not for regular old sine. The amplitude is the average of its maximum and minimum values. Well, no, the maximum is 1, the minimum is -1, and the average of the max and the min is going to be 1 plus -1, which is 0 divided by 2. So that's saying that the amplitude is 0. That doesn't make sense. 3, the amplitude is the distance between the horizontal axis and the minimum point, which is there. Now, before you go screaming and saying, isn't that -1? Nope, distance is positive. So this works just fine. So 3 is going to be my guy for that one. On which interval or intervals of the graph of f of theta equals sine theta is the rate of change increasing? Now, first things first, what does rate of change increasing mean? Concave up. So let's graph this is just regular old sine theta. So let's graph what regular old sine theta looks like. We know sine theta starts at 0, 0, comes up to 1, bottoms out at -1. So starts at 0, 0, peaks out at 1/2 a pi, comes back down to the x-axis at regular pi, bottoms out at 3 pi over 2, and then comes back up to repeat the process at 2 pi. So it looks like this. Starts here, hits the top, comes back down, hits the bottom, comes back up, repeat. Now, the most basic answer would be saying, concave up is going to be at pi to 2 pi. But here's the thing. I don't know if this answer is going to be good enough. Okay, why? Well, if it was good enough, we would just be like, this doesn't repeat, therefore, like, it's only going to be that. But this is a repeating thing. So this is what I have to do. Whenever it repeats, attach a k to it. Now, if I were to let k be any integer, then this makes sense because this would repeat if k was 1 at 2 pi, and if k was 2, then 4 pi, and if k was 3, then 6 pi, so on and so forth. How do I set this pi up to make sure that this pi is pi and 3 pi and 5 pi? Well, make this 2k minus 1. So when k is 1, I get 2 pi, and this is 2 minus 1, regular pi. And when k is 2, I get 4 pi. And so this would be 4 minus 1, 3 pi. So that would work out nicely throughout. So since this is a repeating function, since it's sinusoidal, we have an infinite amount of answers, and that's how we're going to write it out. Determine the general expression for the input value of all points of inflection of the graph g of theta equals cos theta. If you don't remember what a point of inflection is, or an inflection point is, wherever your graph changes concavity is when you have an inflection point. Okay? So let's graph cosine. Let's graph cosine. Cosine starts up here at 1, bottoms out at -1. It starts up here, hits the x-axis at pi over 2, bottoms out, comes back up to pi, comes back up and hits at 3 pi over 2, and then repeats the process at 2 pi. So, the input value for all the points of inflection are basically where we see this change in concavity, like here. So like 1, or half a pi. Well, that was a close one. So half a pi, 3/2 pi. Basically, every half a pi plus 1. So let's set it up like this. Y equals half a pi plus 1k, where k is any integer. Okay, that's going to be the input value. Half a pi plus 0 is going to be half a pi. Boom. Half a pi plus 1 is going to be 3 pi over 2. Boom. And then so on and so forth. So this will give us like a nice little equation to give us the points of inflection for any inflection point. Crazy problem, but, we did it. Identify the statements that are true due to the fact that the cosine is an even function. Let's remind ourselves what an even function is. An even function is basically whatever you do on the left side of the y-axis, the right side has to be a mirror image of it, which I probably demonstrated that poorly because I decided to make this weird squiggly line. We know cosine looks like this. Now, I'm not going to go crazy drawing this out, but we know it looks like this, which means the other side looks like this. There's our even function. So the graph of y equals cos theta has a rotational symmetry about the origin. No, that's what makes it odd. The graph of y equals cos theta has a reflective symmetry over the y-axis. Yes, that's what makes it even. Now, you may also remember a fun fact about an even function, that f of negative x is going to end up equaling f of x. Now, what that means from a graphical point of view is if I plug in like negative whatever, negative a, I'm going to get the same exact thing as if I were to plug in regular a. Okay, now what that means in a case like this is if I have basically g of negative x, or let's just say g of x equals cos x. G of negative x means cos negative x. So cos negative x, if these guys are allowed to be the same, is going to equal cos regular x, which is what 3 says. What this guy is saying is the rule for an odd function. What this guy is saying, if I plug in like negative a value, I will get the opposite than if I plug in the positive value. Like if I plug in negative that guy, I would get this guy, but down here, which is not what happened at all. That is the odd format. So 1 and 4 follow odd rules, 2 and 3 follow even rules. The daily low temperatures of a certain city over a period of time are modeled with a sinusoidal function, the xy plane. That doesn't seem grammatically right. The minimum daily low temperature is 24 degrees Fahrenheit, and the maximum daily low temperature is 52 degrees Fahrenheit. Based on these temperatures, which of the following is the best value for the amplitude of a sinusoidal function? Well, basically, if you're given a sinusoidal function, something that looks like that, but maybe better drawn, the sinusoidal function's amplitude is the very tippy top to the very bottom, this minus that, but then you divide it by 2. So it's whatever the maximum value is minus the minimum value, and then divide that number by 2. So kind of like the opposite of the average. So in this case, the maximum is 52, subtract out 24, and then take that guy, divide it by 2. 52 minus 24 is 28. 28 divided by 2 is 14. So there it is. There's your amplitude. The figure shows the graph of a periodic function f in the xy plane. What is the frequency? So this is kind of doing backwardsy things. So let's put it this way. Usually when you're given a function that is a sine, the number in front of your angle, so if it was like sine 3x, that 3 is your frequency. However, the frequency is not the period. They're not the same thing. The way you calculate the period is going to be 2 pi over your frequency. Now, I don't want the period. I want the frequency. So if we, divide both sides by p and multiply both sides by f, you get basically the same exact function where 2 pi divided by the period will get you your frequency. So let's find the period. The period is how long a cycle lasts. So if we take the tippy top of this 2, right, and find the other tippy top, which appears to be 10, it looks like the period is 8. So if the period is 8, the frequency is going to be 2 pi over 8. 2 over 8 simplifies to 1 over 4. So the frequency is going to be pi over 4, which is u. All right, we are in 3.6 here in AP Precalculus land, and in 3.6 you are now going to do some manipulation of sinusoidal functions. So a sinusoidal function looks like this. You got y equals a times, this is a sine, so we'll write out sine. When it's cosine, we'll write out cosines. Okay, b times x. And tell you what, we'll leave it like this. This is what this looks like, so we'll leave it like this. We won't write out the whole c and d thing. We'll do that in later problems. What a here stands for is a stands for the amplitude. That's how tall something is. Okay. What B here stands for is B stands for, that's an ugly looking arrow, the frequency. Now the frequency, okay, the frequency is the same exact thing as 2 pi over the period. So if I want to find the period, we can find the period by doing 2 pi over whatever that B is. Okay, so let's do a little bit of math. First things first, before we even graph, the amplitude is the number in front of sine, and in this case, the number in front of sine is 4, so the amplitude is 4. The midline. Now, the midline is basically when you graph this thing, the midline is when you cut it directly in half. When you're not adding or subtracting anything to the whole thing, your midline is the x-axis. Okay, the midline is found by whatever number you add to this whole sinusoidal function. I'm not adding anything. So the midline is nothing. So the midline is the x-axis, so we will say the equation y equals 0. Now, what that looks like graphically is since everything starts out in the middle, since everything is leveled off at the x-axis, my amplitude is also going to be my maximum value and my minimum value. Since I have no vertical shift, my maximum value is going to be 4, and my minimum value is going to be -4. My frequency is the number in front of x. Well, the number in front of x isn't as clear because it's x over 2. But I know I can write this guy as 1/2 x. So B, my frequency, is 1/2. Now, I can find my period by doing P equals 2 pi over 1/2. Now, I don't like dividing by a half, so let's multiply the top and the bottom by 2. You're allowed to do that because you know it equals 1. So that's going to cross that out, because a half of 2 is 1. And 2 pi times 2 gives me a period of 4 pi. Now, given all this information, it's time to graph this puppy out. Okay, sine starts out at 0, 0. Since I'm not shifting this thing left or right, and I'm not shifting this thing up or down, it starts still at 0, 0. Everything repeats at 4 pi. Okay, now I don't have 4 pi to take it to. Okay, I only have 2 pi, which means when I hit 2 pi, I go through half of its process. So what's going to happen is the whole thing would look like this. Start here, go up, go down, and repeat. And it would repeat at 4 pi. But since my graph only takes me to 2 pi, I'm cutting it off right there. So this is going to peak out halfway between 0 and 2 pi, which is pi, and it peaks out at 1, 2, 3, 4. And then it goes back to its midline at 2 pi. Now, similarly, going backwards, this thing is going to bottom out at 1, 2, 3, -4, and then hit the x-axis again at -2 pi. So when I draw that out, which I'm terrible at, it's going to look like this. Remember when I said I'm terrible at it? I wasn't lying. Started off weak, ended off strong. But that's it. Let's get rid of this one. I'm not happy with that one. I'm just going to scooch it over there and make it look slightly better. So there you have it. There's your sine. There's your sine. As you can see, the whole period is seen just on this graph. Amplitude is 4, -4 is minimum value. Everything is exactly as it should be. Midline is y equals 0. Yeah. It's our first sinusoidal graph that we ever did here on random AP Precalculus Problems that I stole from the internet. I do have random SAT ones. You should check those out too. Like and subscribe. Write the equation of the cosine curve. All right, before we try to come up with an equation, let's try to remember what cosine looks like. Cosine, give or take, is going to be starting at 1 and then coming down and repeating itself at 2 pi. What I need to do is I need to take a look at this and see how this differs from the regular cosine curve. What I see right off the bat is, first things first, I am not centered at the x-axis. I am moved down, looks like 1 whole unit. Also, things are kind of like squeezed a little bit, and my period is different. So I'm looking at 3 things that are off. Okay, so let's take a look at thing number 1. Thing number 1 is my amplitude. That's probably the easiest thing to look at. My amplitude is going to be the highest point minus the lowest point, and then take that guy and divide that by 2. Now, my highest point appears to be at -1/2, and then my lowest point appears to be at -1.5. Which means the difference between -1/2 and -1.5 is 1 full unit. Does that mean my amplitude is 1? No. My amplitude is going to be half of that. So half of 1, let me get out my calculator, is a half. So that's going to be my amplitude. That's thing number 1 that I need to focus on. Thing number 2, probably the other easy thing, quote unquote easy thing, is to figure out where my midline is. What my midline does is that gives me the vertical shift. Now, my midline is literally me taking a line and cutting my cosine in half. Now, that appears to happen right around here. Now, what my midline does is my midline tells me where my vertical shift is. Okay, so my vertical shift, and I'll write this out as VS just because I don't have all the space in the world, has me moving down 1, okay? Or I'll write this out as a vertical shift of -1. How will that affect my cosine function? Well, after I do all of my cosine stuff and the things attached to cosine, I'm just going to subtract 1 to it, and that takes the whole thing and moves it down 1. Okay, so that's going to be my vertical shift. Last thing is, since my cosine kind of started out, my peak was where it should be, I don't have a phase shift or a horizontal shift, so thank God I don't have to worry about that. However, what I do have to worry about is my period. Now, my graph is supposed to repeat every half or every 2 pi. That doesn't happen here. My period is every 1 pi. So if your period is every pi, period is also given to you by figuring out what your frequency is. Now, frequency, when written out, is the number attached to x. The way you find out what your frequency is you take your period and you do, and I like to call, by the way, I like to call my frequency B. It's going to be 2 pi divided by the period. The period is pi. So this is going to be 2 pi divided by pi. Pi's cancel out. So my B, or my frequency, is just going to be 2. Okay? So let's write all of this out now that we know what we know. Okay? Y equals, my amplitude is going to be the number in front of cosine attached to cosine, and my amplitude was a half. Cosine is cosine. My number attached to x is going to be my period. So, I'm sorry, my frequency. So my frequency gives me 2x. And then since this is bumped down to 1 unit, since the midline is at -1, I'm subtracting 1 from this whole thing right here. So that's my cos function. When we deal with phase shifts and horizontal shifts, things change and it makes things a whole lot messier, but thankfully we didn't have to deal with that here. Just the other 3, dunzo. All right, we've got ourselves a calculator problem, but looking at this, I'm not sure we really need to step aside and use a calculator. We'll do a quick calculation here, but I don't know if we need to do one of those side screen or split screen things that I always do. We'll see. The cycle between low tides and high tides at a beachfront town can be measured by blah, 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 sinusoidal function without the phase shift, where A, B, and D are constants. The maximum value of the tide is 12.04 feet, and the minimum value of the tide is 1.36 feet, assuming we know the values of B and K. I don't know what K are. Which of the following would best define f of x? So what we do have is the amplitude. What we don't have is the frequency, and surprisingly, we don't have the vertical shift, which we could find given this information, but all they seem to care about is the amplitude, which means, again, the calculator is not super necessary. The way you find the amplitude, if given a sine or cosine function, is you have your function, right? At some point you peak out, at some point you bottom out. So whatever the maximum value is and whatever the minimum value is, the amplitude is going to be the max minus the min, but then you take that whole thing and divide it by 2. Okay, now what that does is that also gives you an idea of where the midline is going to be, which is what D would be, but we're not being asked to find that, surprisingly, in this problem that I stole from the internet. Now the maximum value is 12.04. The minimum value is 1.36. Take that, divide that all by 2, which is probably why they want a calculator, but I'm just going to use good old Siri. What's 12.04 minus 1.36?
The answer is 10.68.
So you got 10.68. I don't need Siri for this one. Dividing that by 2 gets me 5.34. So my amplitude is 5.34. My amplitude is my A. So that tells me that the only logical option here is going to be D. Again, I could use this information to find out where the midline is, and the midline would be somewhere in the 6s. And these guys are 6 right here, so that's probably where, they use those as examples. You would find that by doing the average of these two numbers, but we didn't have to do that, just the amp. Create a sine function that has the following attributes. We have amplitude of 3, period of pi, phase shift left of pi over 8, and a vertical shift of down 4. Let's write out the formula for sinusoidal functions before we get started. Pretty big problem. We have y equals, this is a sine, so we'll use sine of b times parentheses x minus c, close it, plus d. Now let's take a look at what every little part means, okay? A is amplitude. All right, so in this case, that makes life pretty easy. B is attached to x, but if we also have a phase shift, B is going to be outside of the parentheses where x is being manipulated. B is the frequency, okay? B is the frequency. Now, if I wanted to find out what B is, I have to find out the period, and the frequency can be found by doing 2 pi divided by the period. Okay, so this period is pi. I'll do a little bit of quick math right there to take care of that when I have to take care of that. C is going to be my phase shift. Now, when I'm moving left, the number in the parentheses is positive. That's why the negative here is given. When I'm moving right, the number in the parentheses is going to be a positive number. So left pi over 8 means I'm actually going to add pi over 8, but we'll get there when we have to get there. D is going to be my vertical shift. Okay. So the little bit of math that we have to do before we could start plugging things in is going to be for my frequency, for my B. Now again, frequency is found by doing 2 pi over the period. the period is pi. 2 pi over pi has the pi's cancel out, and so b is going to be 2. So I have my a is amplitude, my b is 2, my phase shift means I'm going to have left pi over 8 is going to be x plus pi over 8 because it's opposite land whenever you're dealing with inside the parentheses with x. It's always been like that for, it seems like, every single AP Precalculus problem. A vertical shift of -4 or down 4 is going to be a vertical shift of -4. So I kind of accidentally spoke that into existence. So let's write all of this out. Y equals my amplitude, which is 3, sine, parentheses, b, which I found out to be 2, parentheses, x, since left is going to be my phase shift, plus pi over 8. Close the first parentheses, close the second, and since I'm moving down 4, is going to be -4. Yeah, so not the prettiest problem in the world, but this was pretty straightforward, and the only little bit of math that we had to do was for the frequency. And we just have to be careful with phase shifts because they're backwards when it comes to these types of problems. All right. We are being asked to find the sine and the cosine function of this graph right here. Now, this is a sinusoidal function, and it's not at all what it should look like if we know what sine and cosine looks like. So let's do the sine first and hope that when I do the cosine part, a lot of things repeat. Here's a hint, it will. This is what I know sine looks like. Okay, this is what I know sine looks like. I know sine starts at 0, 0. It peaks out at 1, it bottoms out at -1, and it repeats itself every 2 pi. So peaks out at 1, bottoms out at -1, and repeats at 2 pi. We don't have that. We don't have that at all. So what I'm going to do is I'm going to look at this picture and try to figure out where the starting point would be and go from there. So if I were to start halfway in between the top and the bottom, where it starts to curve up, where it starts to be concave down, it looks like a good starting point would be right there. So now what I'm also going to do is write out the general forms for a sinusoidal function when using sine. Okay, that form is y equals a times sine, where I'm multiplying inside b times x minus c, close it, plus d. A is the amplitude. Okay, pretty easy to find, generally speaking. B is the frequency. I'm going to have to do a little bit of math. C is going to be a phase shift, which means horizontal, which means left and right. Keep in mind, whenever you're dealing with stuff inside the x part of the parentheses, everything is backwards. And then you have plus D. And D is going to be a vertical shift, just like it seems to always be whenever we deal with adding stuff outside the parentheses. So let's see what we have first. Let's start out with the amplitude, because that's usually the easiest to find. The amplitude is found by doing the very maximum and the very minimum, so A. Now taking that maximum number, which is 2, minus the minimum number, which is 0, subtracting that and dividing it by 2. The amplitude is not the top minus the bottom, and it's the size of the whole thing. It's half of the whole thing. So that's where we kind of get this average-looking formula from. 2 minus 0 is 2. 2 over 2 is 1. So the amplitude is 1, which means life is easy. I don't have to write that really difficult number. B is found by doing the frequency, which in order to do the frequency, I need the period. Now, the period is where this wave process repeats. So what we need to do is we need to find an obvious spot where this repeats. So it looks like the very top of the wave and the very top of the wave happen here. So the period can be found, that's not how you spell period. The period can be found by doing this right side here, which is 5 pi over 2 minus the left side minus 7 pi over 2. So we have a double negative, make it positive. 5 pi plus 7 pi is 12 pi. 12 pi over 2 is 6 pi. Now, does that mean b is 6 pi? No, no, no. You find b by taking 2 pi and dividing your period. 2 pi divided by 6 pi's, pi's cancel out, b is a third. Okay? There you have it. Now, what I have here is my starting point is now this guy right here. That's kind of like my new origin. How do I get to that new origin? Well, I have a positive phase shift. I'm moving to the right what appears to be pi. So when you move to the right what appears to be pi, what you're actually doing is you're doing x minus pi. Remember, when you move to the right, it's the opposite of what it appears to be. So my parentheses is going to be x minus pi. The way that you find d is found by doing the midline, which I kind of already created, but let me write it out a little bit further. The midline is the horizontal line that cuts my wave in complete halves. Wherever that goes through, whatever y value that horizontal line is going to be your midline, which is going to be your d. So in this case, d is 1. Now I have enough information to put all of my sine stuff together. Y is going to equal an amplitude of 1, which is invisible 1, don't need it, sine. My b is a third, parentheses, x minus pi, because it's right 3, close it, and my d is positive 1 because I shifted up 1. That's my sine. Now I need to find my cosine. And if you're like, oh no, I have to start over. Nope, because with the cosine, the amplitude will be the same, the midline will be the same, and the period and the frequency will be the same. So the only thing that changes is this guy right here. So let's kind of get rid of you. You're now dead to me. I don't need this picture anymore. And I'm going to rewrite this equation and sneak the word cosine in there if I can make it look pretty enough, and I just did. So cosine. All right? What does cosine look like? Well, cosine starts up here at 1, goes through half a pi, bottoms out at -1 at pi, and then repeats itself at 2 pi. Okay, repeats itself at 2 pi. So where can I find a peak to start at? How about here? That is a peak that I can start at. Okay, so how can I get to that guy there? Well, I can get there by going right 5 pi over 2. Now, if you're confused and if you're wondering, well, couldn't I use that guy right there? I sure could. The nice thing about periodic functions is they repeat themselves, and so it doesn't really matter which peak that I choose, so I'm choosing this one right here, 5 pi over 2. So 5 pi over 2 is the only difference that this is going to be. So everything else is going to stay exactly the same, but since I'm phase shifting right positive 5 pi over 2, that is going to be x minus 5 pi over 2. These guys stay exactly the same, except for this guy, and now I'm calling it cos. So y equals the amplitude of 1, so invisible 1, cosine, my frequency didn't change because my period didn't change, x minus 5 pi over 2, that's the only thing that did change. My midline didn't change, so it's still plus 1. And there you have it, sine and cosine functions. You can't spell functions without fun, and that's what this was. So like and subscribe. All right, we've got ourselves a really important problem here about Ferris wheels. You will see problems like this all over the place. Suppose you are riding a Ferris wheel. After every one is loaded, the wheel starts to turn and the ride lasts 180 seconds. your height h in feet above the ground at any time t in seconds can be modeled by the equation h of t equals 85 sine pi over 20 times the quantity t minus 6 close plus 90. So we've got quite a few things going on here. We see a Ferris wheel that revolves around. At certain points, it's probably going to repeat the process. So if you're here, you're going to hit this spot several times over the course of 180 seconds. You start out a certain amount of feet above the ground. You peak out at a certain amount of feet above the ground. Lots of stuff going on here, and we're going to end it by doing 2 calculator problems. So let's begin with what is the period. You don't look at this and see the period right away. This guy right here is the frequency. So if you're given the frequency, which is the number multiplied to t, or in this case, the number multiplied to the quantity involving t, the period is going to be found by taking 2 pi and dividing that frequency. So 2 pi over 20. Right? In order to get rid of a lot of this stuff, we're going to multiply the top and the bottom by 20 over pi. Multiply the top and the bottom by 20 over pi. The reason why we do that is it gets rid of all of this. The pi's also cancel out, and you end up with 2 times 20, so the period is going to be 40. So the period is how long it takes to complete one full cycle, or in this case, one full spin around the Ferris wheel. So what does the period represent? Well, the period represents the fact that it takes 40 seconds to complete a cycle, or in this case, a revolution. Sounds a lot more barbaric than it needs to be. What is the frequency? Well, the frequency is just that number right there. Just that number right there, pi over 20. Now, what does that pi over 20 represent? Well, the pi over 20 represents that little bit of change every 40 seconds. That little bit of change. So we can view this as one of 2 ways. We could view this as the distance traveled along the arc, or the central angles change. So I'll do that. What does the frequency represent? The angle measure changed per second. Okay? So like this would be the central angle. It goes pi over 20, pi over 20, pi over 20, pi over 20, and it takes 40 of those. 40 pi over 20s gives you 2 pi, which means one full spin around the circle. 40 times pi over 20 is 2 pi, which tells you a full spin around the circle. And again, you can also say arc length measure or stuff like that. But you don't have r, although we could find it, but I'm not going to go that far. What is your maximum height? Well, let's get rid of this. Let's clean this up a little bit. What we do know is we know that 85 represents the amplitude, okay? And 90 represents the midline. So what's going to happen is you have a midline right here at 90. The amplitude is not the very tippy top to the very bottom. It's the distance from the midline to the tippy top and the distance from the midline to the very bottom. So since the amplitude is 85, that means we're going to have a maximum height somewhere here at 85 plus 90. And then we're going to have a minimum height at somewhere minus 85. So the maximum height is going to be 90 plus 85, which is 175 feet. And the minimum height is going to be 90 minus 85, which is going to be 5 feet. And then you can prove the fact that the amplitude is 85 simply by adding stuff to that stuff. I just kind of lost my train of thought. Forget it. How many circles will the Ferris wheel make during the ride? Well, if the whole ride is 180 seconds, right? And it takes what is it, 40 seconds per circle, per revolution? Well, then 180 divided by 40 is going to be 4.5. So 4.5 circles. So if you start around here, you're not going to end here. You're going to end here at literally its opposite, which is going to be convenient for us to do H and I. Now, what I'm going to do for H and I, and I'm going to do this both in one problem so I could just kind of get it all out of the way, is I'm going to answer these in one. I'm going to type in that equation into a calculator, and it's asking us how high we are when the ride begins. So what that means is I take this equation and I find out what happens when t equals 0. Then I'm being asked how far off the ground are you when the ride stops. I care about when t equals 180. So I'm going to do both of these in the calculator at the same time. I'm going to type that guy in. I'm going to find out when t is 0, and I'm going to find out when t is 180, and I'll be right back, and we'll see what we get. All right, let's kill two birds with one stone. Make sure your mode is set to radians. It is. We're good. We're going to graph this in y equals, and we're just going to use it that way instead of plugging in normal numbers. 85 sine instead of well, we do have pi. Where is the pi button? Pi is that guy right there. Pi over 20, open parentheses. Instead of x, we're going to use t, or instead of t, we're going to use x, minus 6, close it, plus 90. Now, we're going to graph it. We're not going to get a whole lot. Okay, not going to help us at all. What we're going to do is we're going to go to Window, and we're going to change things to where we care about. We know that our x, which is our t, happens between 0, so we'll keep it at -10, 0, and 180, so we'll stretch it out to 200 just for funsies. We know that our y minimum, we found out that our minimum height was 5, so let's keep this at 0. And our maximum was like 175, so let's bump that up to 200 just for fun. Now when we hit graph, we see what we need to see. Okay, we care about two things. We care about what happens at 0, and we care about what happens at 180. So at 0, I can do this second calc value. You could have also gone to your table and gotten an answer right away, but I'm doing this way. And by doing it this way, I get 21.2335. So that'll round up to 21.234. That's when x is 0. I'll write that out in a minute. When x is, or t, same thing, is 180, we're going to do the same thing by going to second trace, type in 180 after hitting value, and that gets me 158.7664, so 158.766. So let's take those two values and plug them in or write them out in our thingamathing. So when t was 0, we ended up with 21.234, and that's how high we are off the ground. So, you know, we're somewhere right around here. We're obviously not the first person on the ride. We're somebody right around here when the ride begins. When the ride ends, we're literally at the opposite end here, which ended up being 158.766 feet. Okay, so there you have it. Pretty exciting stuff. The reason, by the way, another fun fact why these numbers make sense and why we are polar opposites, you add these two together, you get 180. And 180 is the distance from the maximum to the minimum, which is what I was trying to say over here, if my words could actually, you know, put their words together like just now. But this is a very important problem that you will see a lot over AP Precalc tests, practice tests, maybe the real test, we'll see. But yeah, it was fun. Identify the functions that would have a graph that is identical to the graph of g theta equals cos theta minus pi over 4. All right, before we do anything, let's draw out the most basic version of cosine. Okay, cosine starts up here, bottoms out, peaks out at 2 pi. This guy is shifted to the right pi over 4. Now, that's a negative, and if you're wondering, why is it shifted to the right? Well, a negative number inside the theta or the x of a cosine, the negative number represents a positive horizontal shift. It's opposite land in here. It always is. So this guy is going to end up looking something like that. So I need to figure out which one of these do that. Well, cosine has a period of 2 pi. So these guys aren't going to look the same until I hit that 2 pi mark. So what I can do is I can take each of these guys, each of them, and I can add or subtract 2 pi to that number right there, because by adding or subtracting 2 pi, I'm not changing the look or the shape of this because these guys are periodic. So I'm going to take one, I'm going to add 2 pi to negative 9 pi over 4. Now, adding 2 pi to negative 9 pi over 4 is the same thing as adding 8 pi over 4. I think you can see why. And if you add 8 pi over 4, you get negative pi over 4. So cos theta minus 9 pi over 4 is the same as cos theta minus pi over 4. Which is that? So 1 is an option that works. Similarly, 2 gives me another cosine where it's theta plus 7 pi over 4. I need to see if I can make that the same as negative pi over 4. So I'm going to take 7 pi over 4 and subtract 2 pi, or subtract 8 pi over 4. 7 pi over 4 minus 8 pi over 4 is no way. Negative pi over 4 again, which is what I want. So 2 works. Interesting. Now, this one's a little different. As you know, sine, the difference between sine and cosine is sine starts out at 0, 0, where cosine starts at negative 1. That is a difference of a period of pi over 2. In other words, cosine, if I were to take cosine and move it to the right pi over 2, right? Move it to the right pi over 2. If I take this whole thing and move it to the right pi over 2, right, this guy will come back down and hit 0, 0 and give me sine. So cosine pi over 2 is the same exact thing as sine x. Okay, cosine x minus pi over 2 is the same as sine x. Sorry for misspeaking there. Now, what that means in this situation is I'm given sine pi minus 7 pi over 4. Okay, sine of theta minus 7 pi over 4 can be rewritten as cosine theta minus 7 pi over 4, right? Because, you know, we're imagining that this is x minus pi over 2. I can rewrite this as negative 7 pi over 4. We'll leave that. Multiply the top and the bottom by 2 over 2 minus 2 pi over 4. And this gets me cosine theta minus 9 pi over 4. Wait a minute. That's the same as you. Wait a minute. So this guy is the same as that guy, which is the same as that guy. They're all the same graph. Well, would you look at that? Isn't that neat? It is. It's very neat. The graph of f of theta equals a cos theta plus d contains the points pi, negative 1, and 2 pi 7. What is the value of a? So you're trying to find the altitude given this information. Well, good news. We don't have any b or c here, which means in this case, the frequency is 1. And if the frequency is 1, the period is the standard 2 pi, which is good news. Now, why does that affect us? Well, let's try to graphically look at the 2 points that I am given. Okay, the 2 points that I'm given happen at pi and 2 pi. Okay, Pi is -1 down here somewhere, and 2 pi is 7 up here somewhere. Okay, now the thing is, if the period is 2 pi, then this thing completes a full revolution here at 7 again. Not that I need to know that, but if the period is 2 pi, that means this guy starts at 7. So this guy, oh boy, this guy is half of its revolution. So you're a minimum value and you're a maximum value because of the fact that I gave you half of a pi or half of the period, which tells you where the max and where the min will be. So the min is at -1 and the max is at 7. Why is that good? Well, A in this case stands for amplitude. And the way you get the amplitude is the distance between the top and the bottom divided by 2. The distance between the top and the bottom divided by 2. So 7 minus -1 divided by 2 is 7 plus 1, which is 8, divided by 2, and therefore the amplitude is 4, which means A is 4. A spring oscillates up and down, and its displacement from the equilibrium position is modeled by the function s of t equals 5 cos pi over 4t, where t is time in seconds. What's the amplitude? The amplitude is just the number attached to cosine, so the answer is 5. Well, thanks for watching. I hope you enjoyed this. Like and subscribe. A population of rabbits in a certain forest can be modeled using a sinusoidal function of time. A minimum population of 500 rabbits occurs at month 3. The next maximum population of 540 rabbits occurs at month 9. What is the period of the sinusoidal model? Okay, so it starts out by saying, at 3, you have 500 rabbits. Okay, 500 rabbits. And then it says the next maximum, which is key, happens at 9. And that maximum is going to be 540 rabbits. So 540 right there. So if this is sinusoidal, you're going to look like this, which means this is half of a period. So to complete the process, if it takes 6 to get half of a period, that means the next half of the period, or to complete the period, you're going to add 6 to 9, which is 15. So this guy can come back down and complete its cycle at 500 again. Okay, so what is the period of the sinusoidal model? Well, 15 minus 3 gives you a period of 12. 12 months. A year. For those of you who don't know what 12 months is. A sine curve has a maximum point at 12,4 and a minimum point at 20, -10. Which statement is true? All right, let's try to graph this out. I have positive x's and something that is kind of big and not big at all. So I have 12, 4 up here. I have 20, -10 down here, not drawn to scale. So this is a sinusoidal model, looks like that. They care about amplitude. They care about vertical shift. Let's take a look at amplitude first. Amplitude is the maximum minus the minimum, but half the distance. Okay, so the maximum and the minimum, half the distance. So I'm going to take 4 minus -10, gives me a total height of 14, and then divide that by 2. So double negative makes a positive. 14 over 2 is 7, so the amplitude is 7. The amplitude is 4? No. Amplitude is 14? No. So neither of those. Vertical shift. Now, the vertical shift is if I take my line and move it up or down. A vertical shift is also found at a place called the midline. The midline is if I were to take this graph and try to estimate where this guy cuts it in half. Now, I don't have to estimate because the midline happens directly in between the y value and the other y value. So the midline is going to be the average of 4 and negative 10. Okay, and technically it's the equation y equals that because it's a horizontal line. So 4 plus negative 10 is negative 6, and negative 6 over 2 gives me the equation y equals negative 3, which means if I were to create a sinusoidal function, I get blah, 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 minus 3, which means the vertical shift is negative 3. So yes to you and no to you. And that's it. A cosine curve has a maximum point at 516 and a minimum point of 76. Determine the product of the amplitude and midline values. So this is kind of a strange problem. Everything exists in quadrant 1, so let's kind of get a little graph going on here. Max point is 516, so we'll draw that up there. Minimum is way over here at 17.6, so we'll draw that there. This guy is going to look something like this. Okay, now we are dealing with amplitude and we are dealing with midline. Let's take a look at amplitude first. The amplitude is the distance between the tippy top to the very bottom divided by 2. Okay, so the tippy top is going to be 16 minus 6 gives me the total height, and then we're going to divide that by 2. So that is going to be 16 minus 6, which is 10. 10 divided by 2 is 5. That's our amplitude. Now our midline is basically a horizontal line that cuts our curve into half. Okay, so our midline is going to be the equation that cuts through the middle of my maximum and minimum value. In other words, it's going to be the average of my maximum and minimum value. You find average by doing 16 the maximum plus 6 the minimum, and then divide that by 2. Okay, 16 plus 6 is 22, the Taylor-Swift special, and then when you divide that by 2, you get 11. So that's my midline value, and my amplitude was 5. They want me to find the product of the amplitude and the midline value because AP Precalculus just has to complicate things. The product is going to be 5 times 11, which is 55. So there you go, a pretty basic problem where they had to complicate it at the very end. A Ferris wheel has a radius of 30 feet and rotates counterclockwise at a constant rate. The height in feet of a rider above the ground after t seconds can be modeled by the function h of t equals 30 sine pi over 15t plus 60. What does the 30 represent in this function? Well, the 30 is the number attached to sine, which is the amplitude. Well, this was fun. Thank you for watching, like, and subscribe. The graph above shows function f of x equals sine bx and 4 points from a data set. Determine the value of c that would make the graph of g of x equals a sine times bx plus c a good model for the data set. Basically what they're looking at, okay, is they're basically saying, look, we have these points and we need to try to make it fit this sine graph. So we need this graph to move over a little bit so it fits nicely. How many units do I need to make this graph look over so it fits the 4 dots? Well, if I move this graph 1, 2 units over, that should fit pretty nicely if I knew how to draw a straight line. Okay, so I need to shift the blue line left 2. This is a horizontal shift in a negative direction. Now, when I move left 2, that is actually inside the parentheses a positive change. So what's going to happen here is the difference between this guy and this guy is nothing except for the parentheses is going to be x plus 2, because when I move left, it's a positive change inside the x-axis, or the x parentheses. So this becomes x plus 2. So a good C value would be C equals 2. The data set below can be modeled by the function g of x equals a cos b times x plus c close plus d. So the typical sinusoidal function, usually you're given a minus here, but this is giving us a c. That might change things a little bit. A, b, and d have the same values as function f. So f and g, and what is f? The data set? I guess f is the data set. The only difference is a horizontal shift. Okay, so this is what I need to look at. This is what I need to look at. I need to determine the value of C that would produce a model for the data set. This is cosine. Cosine typically looks like this. Okay, you have your maximum here, then you bottom out and you rotate and blah 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 blah. But your maximum starts at 0. Looking at this data set, I go from 17 to 20 to 23 to 26 to 29, and then I have y values of 7.9, 6.4, 5.8, 6.4, 7.9. So 7.9 represents my maximum, and my maximum happens at x equals 17. So basically, this picture is the same as this guy, where this guy is way over here at 17. So I need to move this graph over to the left 17 units. If I move to the left 17 units, that means I'm only affecting this guy right here. Now, a horizontal shift that is negative appears positive inside the parentheses because it's opposite here. So what's going to happen is my C is going to be positive 17 in order for me to take this guy right here, this data set right here, and match a typical cosine function. Okay, so again, the thing that you need to remember here is that when you move left 17, it stays positive inside the parentheses because inside the x parentheses is opposite land. Crazy. Assume the following data set can be modeled by a sinusoidal function. Estimate the value for the midline of the model rounded to the nearest integer. All right, what I have to do is I have to run to a calculator, throw that in, do sine reg, and use that information to find the midline formula to the nearest integer if I have to do that. I really don't even need, never mind, I'm going to do it anyway. Just watch the video. All right, sinusoidal regression. Let's go to calc, let's go to edit, let's go to stat, and let's go to edit. And let's type in these numbers. 1, 2, 3, 4, 5, 6, 7. All right, we have 7.7. We have, I always feel bad for people who are, just fast forward like 30 seconds and you'll probably be fine. Unless you want to hear me say numbers out loud and hear typing sounds. Or just fast forward 30 seconds. Actually don't, because I don't know if that has anything to do with my YouTube money. Hopefully I'm doing this right because I'm talking and typing at the same time. Okay. I guess we'll see. All right, those are our values. Now, before we move on, if we're doing sinusoidal regression, we need to know our period, which is between 1 and 7, so our period is 6. Go to stat, go to calc. Will I need this equation later? I don't think I will because I just need the midline, so I really don't. I just need to see what the equation is. So I'm going to go all the way down to C for sine regression. Don't worry about the iterations part. The period was 6, as we said before, and I don't need to store this, so I'm not going to. I'm just going to hit calculate. Now, there's my equation. It's gross, okay? We'll write this whole thing out, but the key thing here is that 32. So we'll explain what that 32 means in a second. All right, thanks for sticking around, those of you who decided that you were going to put up with that. The equation that we came up with wasn't pretty. Y equals 30.010 sine 1.047x minus 1.991, close it, plus 32. Now, I didn't spend a whole lot of time going over this because I didn't really have to. In this case, what I care about is the value for the midline of the model. The midline happens right here at your vertical shift. So the equation for the midline is y equals 32. So not a whole lot of estimating. I mean, there it is right there in its beautiful, beautiful, beautiful form. We have ourselves a calculator problem that I'm not going to use my calculator. You'll see why. The graph of a sound wave is a sinusoidal function that shows 20 complete cycles between the maximum points at x equals 0.3 and x equals 0.4 seconds. What is the frequency of the sound wave? Now, in order to do frequency, we need to find period. So the period basically happens 1/20th between 0.3 and 0.4. If it completes 20 cycles between these four areas, that means 1/20th of a cycle is going to be my period between these two. So 1/20th of 1/10 of a second. So multiplying those guys together, you get 1/200. Now the frequency is found by doing 2 pi divided by that. So the frequency is going to be 2 pi divided by 1/200. Multiply the top and the bottom by 200 because that equals 1. You're allowed to do that. These cross out. These cross out. 2 times 200 is 400. And attaching pi to it gives us our frequency. See, I didn't need a calculator. Wasn't that fun? If the tangent of an angle in a right triangle is 0.75, what can you conclude about the relationship between the lengths of the sides? So let's go back to geometry and remind ourselves of SOHCAHTOA. TOA means that the tangent of an angle equals the opposite side over the adjacent side. Now, this has to do with right triangle trigonometry, okay? So it also tells us that the tangent of an angle is 0.75. So let me rewrite this out as 0.75 over 1 equals opposite over adjacent. By writing it out this way, it lets me do a little crisscross applesauce and do a little bit of cross multiplication where I can say 1 times the opposite equals 1 times the opposite, which is just the opposite. That's going to equal 0.75 times the adjacent. Now, by writing it out this way, we can now say a phrase like, I don't know, the opposite side is 0.75 times the adjacent side. The opposite side is 0.75 times the adjacent side. The answer is A. Now, I know there's other ways that we could do this, probably a simpler way, but, you know, this is me just breaking it down and, I don't know, making it simple in my little mind. In a right triangle, the measure of one acute angle is pi over 6 radians. What is the value of the tangent of that angle? Well, I know it mentions right triangle, but I'm going to view this from the viewpoint of a unit circle, because if you remember, the unit circle gives you parts of a right triangle. There we are. And so the angle that it gives me is pi over 6. Pi over 6 is like right here. Now, I can view this as a right triangle if I call u y and if I call this part x. But most importantly, the angle is pi over 6. Now, if you remember from the unit circle is split up into dot, 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 dot. This is 0, and this is pi, which means pi over 6 is that first dot that I have right there. Now that gives me the coordinate root 3 over 2, 1/2. Now, tangent of theta is given to us by y over x. I know that because tangent is sine over cosine, and if I do a little bit of simplifying, I end up with y over x. So in this case, tangent of theta is going to represent 1/2 over root 3 over 2. So tangent of pi over 6 is going to be 1/2 of root 3 over 2. Now, whenever you have a fraction divided by a fraction, multiply the top and the bottom by the reciprocal of the denominator fraction. So 2 over root 3 over 2 over root 3. That allows me to completely clear out the entire bottom. And it just so happens that these 2's cancel out as well. That leaves me with 1 over root 3. Now, you were probably taught back in the day that you should never have square roots in the denominator, so we rationalize the denominator by multiplying the top and the bottom, the numerator and the denominator, by root 3 and root 3. 1 times root 3 is root 3. Square root of 3 times the square root of 3 is the same thing as the square root of 3 squared, in which case the square and the square root cancel each other out, and we're left with the square root of 3 over regular 3. So yeah, there you go. That's the tangent of pi over 6. Fun stuff. Find the tangent of alpha. Oh, are we talking about me? Now, the tangent of an angle is found by doing y over x. This is a unit circle. The radius is 1. So all I have to do is label u x and label u y and write out that the tangent of alpha is 0.5 over 0.866. Now, this is not a calculator problem, so you wouldn't really be expected to do this. And if you were allowed to use your calculator to simplify this, we'd simplify this, but we're not going to because I don't have the calculator thing. And I have no clue what 0.5 over 0.866 is off the top of my head. Do you? Well, if you do, then you don't need me to do it. So, leave me alone. But do like and subscribe, please, I beg you. Find the tangent of theta. All right, theta is this angle right here. Tangent is given to us by the y over the x value. And so I have a point here, and I can label it x and y. So the tangent of theta in this case is going to be 1.18 over negative 6.9. Now, this is not the regular standard unit circle. This has a radius of 7, but that doesn't really affect us in any way because we have the point. So if you're worried about well, how do we incorporate that 7? You don't, because it's already incorporated in these points by the fact that we have negative 6.9 and 1.18. All right, now this is not a calculator problem, so I'm not going to simplify this because I don't know what 1.18 divided by negative 6.9 is, so I'm going to leave it like that because that's all we have to do in this situation. Thanks for watching. Hope this helps. Use the definition of tangent to explain why y equals tan x has vertical asymptotes at x equals 2k, basketball, minus 1 pi all over 2 for any integer k. Well, what is the definition of tangent? Well, tangent x is the same as sine x over cos x. Now, vertical asymptotes exists when the denominator is equal to 0 as long as the numerator is not equal to 0. So we have to take a look at both of these. So let's take a look at both of these. Let's label sine in red, and let's graph what sine looks like generally speaking. Okay? Keep this very simple. Sine starts right here, peaks out at 1, bottoms out at negative 1. It comes up here at half a pi, and then hits the x-axis at pi, comes back down, hits the x-axis at 2 pi, goes back up, hits the x-axis at 3 pi, and looks something like this. Now, why is this important? Because x is 0 at 0, and pi, and 2 pi, and 3 pi, and stuff like that. That's for sine. Now, if you're like, if we only care about cos x, why are we doing sine? I don't know, just in case there's holes or anything like that. There won't be, but I had fun doing this anyway. Let's do cosine in green, my favorite color. And so let's quick graph what cosine looks like and see where we cross the x-axis there. Cosine starts at 1, bottoms out at -1. So if it starts at 1 and bottoms out at -1, it crosses the x-axis at pi over 2. Then it bottoms out at pi and crosses the x-axis at 3 pi over 2. Then peaks out at 2 pi and then hits the x-axis again at 5 pi over 2, and so on and so forth. Okay, so my zeros here are pi over 2, 3 pi over 2. Since this is periodic and it's going to keep this process, you will notice that there's no overlap between these numbers and these numbers. So cosine hits the x-axis, or in other words, is 0 at stuff like pi over 2, 3 pi over 2, 5 pi over 2. Well, how do I write that out as a general equation? Well, we would say something like pi over 2. And if I needed to, include like, 3 pi over 2 and 5 pi over 2, basically I want to multiply this guy by every single other number, every odd number. How do I write out an every odd number? 2k minus 1 gives me every odd number. So again, if I were to plug in like 1, I would get 2 times 1. 1 minus 1 is 1. So 1 pi over 2, like you. And if I were to plug in 2, then I would get 2 times 2 is 4. 4 minus 1 is 3. 3 pi over 2, so on and so forth. That, when simplified, and that when multiplied to the very top, gives you x equals 2k minus 1 pi all over 2. And so since vertical asymptotes occur when the x values of the denominator equal 0, as long as it doesn't do the same thing for the numerator, these guys are the equation, or is the general equation for the vertical asymptotes of tangent, as long as it's just regular tangent. When it's not regular tangent, it complicates things. But that is how we use the definition of tangent to come up with the vertical asymptotes in that form right there. Fun! Find the slope of the terminal ray with an angle theta equals 3 pi over 4. All right, so I have 3 pi over 4. What's the slope of the terminal ray mean? Well, usually if I'm asked to deal with terminal rays and angles and stuff like that, we have unit circle stuff. So let's draw that out. So, unit circle is right there. Let me scooch this down because I can never get these right the first time I draw it out. Let me see. 3 pi over 4 is 3/4 of my way from 0 to pi. So 3 pi over 4 lives in that middle dot right there. Now, terminal ray means that guy compared to that guy. So that's my theta, and my theta exists at 3 pi over 4. Well, how do I find the slope of that? Well, if this is 0, 0, and I know that 3 pi over 4 on the unit circle gets me negative root 2 over 2 and positive root 2 over 2. If I know that, then I could just kind of use, the slope formula, up 1 over 2. Wait a minute. This is tangent. I'm finding the tangent. Oh, because the tangent of my angle is just y over x. Oh, so tangent is the slope of the terminal ray. Oh, this all makes sense now. So in order to find the slope of the terminal ray, I'm going to find the tangent of that angle right there. So the tangent is found by doing y over x. So tangent of 3 pi over 4 is going to equal my y value, which is root 2 over 2 over my x value, which is negative root 2 over 2. Well, root 2 over root 2 over 2 is 1, so root 2 over its negative self is negative 1. So this is a perfect up 1 over 1 slope. And that kind of makes sense because, again, this guy is directly in the middle. So this lives at a perfect diagonal in between the y-axis and the x-axis. So yeah, I guess that would be a slope of negative 1. Well, interesting how everything ties together. Tangent. We have y equals 6 tangent, parentheses pi over 4, parentheses x minus 2, close it. Now, this is 3.8 of AP Precalculus. And you might be thinking, not too long ago, we dealt with things that look like this. Y equals a, sine, and we're going to turn it into tangent. And then parentheses b, and then parentheses x minus c, close it, plus d. Right? Phase shift, vertical shift, frequency, which becomes period when you do a little bit of math, and amplitude. Now, you might look at this and think, all right, well, the phase shift is move right 3 because the opposite. And you're thinking correctly, but we don't have to worry about here. And there is no d because there's no number being added, and you're right about that too. No vertical shift. Now, the devil is going to say this. The amplitude is 6. But wait a minute. Amplitude is the measurement from the very tippy top to the very bottom. Tangent looks like this when graphed, right? And if I were to multiply by 6 and shift here or there and make it stretch or shrink or whatever, that's not going to change how this looks, really. It's still going to look like that. So what's the distance from the very tippy top to the very bottom? Divide that by 2? Well, it's infinite. So what's the amplitude? There is no amplitude for a tangent function. You be very careful. Now, the period is still the period. That's no different. Okay, B gives you the frequency. So B in this case is going to be pi over 4. The period is found by doing 2 pi over the frequency. So 2 pi over 4. Okay, when you divide by a fraction, just multiply the top and the bottom by the reciprocal of that fraction. You know this. And so 4 over pi divided by 4 over pi, which is the same as 1, allows that to disappear. The pi's disappear, and 2 times 4 is 8, so the period is 8. Okay, so kind of tricky, but, that's tangent for you. G of t equals tangent pi over 2t. Write an equation that gives all vertical asymptotes of g of t. All right, so first things first, why are there vertical asymptotes? Well, tangent is the same as sine over cosine, right? So it's like sine t over cosine t, which means there's going to be times where cosine t equals 0, and you're not allowed to have 0 in the denominator, so that's where the vertical asymptotes come into play. Now, before we try to figure out the pi over 2t part, let's try to understand what a regular tangent function looks like. Okay, tangent, when graphed, looks something like this. Okay, it goes through the origin, it has this weird curve-looking thing, and then it repeats itself, and then it repeats itself, and blah-de-blah-de-blah-de-blah. Now, here is where we have our vertical asymptotes. Okay, there is where we have our vertical asymptotes. Our vertical asymptotes for tangent occur at negative pi over 2 and pi over 2. Okay, so the period of a regular tangent function is pi. Okay, so the period here is pi because negative 2 or negative pi over 2 to regular pi over 2 is pi. Now, the difference between this guy, which I wrote out to be the regular tangent function, versus this guy is the fact that you have pi over 2 attached to your variable. The way you calculate the period for a tangent function, which is different from sine and cosine, is the period of a tangent function is pi over your frequency. So pi over 2. All right. And the way I find the period here is I multiply the top and the bottom by the reciprocal of the bottom, which is u. So multiply u by 2 over pi. So the period here is 2. The period here is regular too because these cross out. Okay, so now what's going to happen? Now what's going to happen is I have a graph that looks like this, right? And since everything's centered, if the period is 2, the horizontal asymptotes are now going to exist at -1 and +1. And then when it repeats itself, it goes through 2, and you're going to still have horizontal asymptotes at 1 and then 3 now. So it looks like the horizontal asymptotes are every odd number. So how do I write an equation for a vertical line through every odd number? X equals is a vertical line. What I'm going to do is I'm going to say 2k, because what that does is gives me every other, and then if I minus 1, it makes it odd. So if I say let k equal 0, then I get 0 minus 1, so x is -1. Let k equal 1. 2 times 1 is 2 minus 1, so 1, so it works out. But I also have to say that k is every integer. So I'll say for every integer k, as I'm running into my other picture there. Not the prettiest problem that I've ever done, but we answered it. So that is an equation that gives all vertical asymptotes for g of t. Sketch the graph of y equals tan 2x plus 3. All right. First things first, I'm looking at two things. I'm looking at amplitude does not change. Amplitude kind of determines like a stretch or a shrink or decompression or whatever. Not worried about that. Thing number 2 is I have a frequency of 2. Now, the way you calculate the period of a tangent function is a whole lot different than the way you calculate the period of sine and cosine. Sine and cosine, you would do 2 pi over your frequency. With tangent, the period is found by doing regular pi over our frequency. So the period is pi over 2. Now, the way I'm going to graph that out is I know that a regular tangent goes through the origin at 0, 0. Notice here I have no phase shift. I'm not moving left, I'm not moving right. So this is going to go through the middle. Now, before I go too far ahead, I do realize that this is going to move up 3, but that's not going to affect the fact that I have a period that is still going to remain the same. Remember, your period gives you an area of where you have vertical asymptotes. Okay, so if my period is 2, or pi over 2, and I still start in the center here, that means it's going to repeat itself every pi over 2. So if I'm starting in the center, half of pi over 2 is pi over 4, and half of pi over 2 is pi over 4. So I'm going to have a vertical asymptote at pi over 4, at negative pi over 4, and then it repeats itself every pi over 2. So move over 2, another one. Move over 2, another one. Move over 2, another one. Okay. Move over 2 units, another one. And when I'm saying 2, I mean like every half a pi. Not every number 2, every half a pi. I should do it. Now, thing number 2 is I have a vertical shift at 3, which means this doesn't start at 0, 0. I'm not going to go to 0, 0 and go up and then go down. I'm going to start at 3 and do the same thing. Okay? So when I start graphing this now, I'm starting at 0, 3 and going like this and going like this. Oh, boy. All right, so this looks awful. So up 3 and then curls down. That looks bad. Up 3 and then curls down. That looks better. 3 and then curls down. That looks... As you can see, I'm not good at this at all. That's an understatement. And I actually kind of screwed that one up. So let's move that over. Let's make you, oh my gosh, and curl down. So on an AP exam, you probably won't be asked to draw this out because clearly it's not fun and it's not easy. But yeah, I mean, I did the best I could, which is not that great.
That's what it looks like. Kind of. Thanks for watching. Sketch the graph of y equals tangent parentheses x plus pi over 2 minus 1. This is what we're looking at. We're not going to see any stretching or shrinking or compressions or whatever you want to call it. We're not going to see any changes in period because there's no number in front of x. So that's thing number one. The period of a tangent function is pi, not 2 pi, so there's a difference. Normally, what a tangent looks like is it goes through 0, 0, if I knew how to draw, and then has vertical asymptotes at pi over 2 and negative pi over 2, right? And then so you would see like, a continuation 3 pi over 2 or negative 3 pi over 2, yada, 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 yada. This is telling me that I have a phase shift. And since it's a positive pi over 2, whatever's inside the parentheses with x is opposite of what you think. Normally you think positive means right, don't you? This means left. So my guy goes through the center of no longer 0, 0. I'm going to move my center to pi over 2, negative pi over 2. So there's my center now. Okay. Boom. Also, I'm subtracting 1. So I'm going to move this center down 1. So this guy is now going to go through at the point negative pi over 2, negative 1. So since I have a period of pi, that means every half a pi to the left and to the right of where it goes through is going to be a vertical asymptote. So every little unit here is a quarter of a pi, so there will be a vertical asymptote through the y-axis. There will be a vertical asymptote through negative pi. And then what I'm going to do is I'm going to bump over 2 so I have my center again. Over 2, vertical asymptote. And then right 2, center, right 2, asymptote. Right to center, right to asymptote. If you sing it, it makes it easier. That's not true because I'm about to botch this. Let's try to make this as pretty as possible. I already failed. Boom. Boom. I'm really bad at drawing these, but you kind of get the idea. Boom. Boom. All right, so that's what it's supposed to look like. Thanks for watching. Shown above is the graph f of x equals tan x. Okay, I see it. Normal looking tan x, period of pi, goes through 0, 0, repeats every pi. I like it. It gives us the interval of negative pi over 2, 3 pi over 2, If g of x is this same exact thing minus 3, what is the equation of the line connecting the inflection points? Well, hold on, time out. So basically, let me try to sketch this. What it's saying is I'm going to have a new function where this is going to be the same exact graph minus 3. What does that mean? That means this shifts down 1, 2, 3. Now, what is an inflection point? An inflection point is where my picture changes concavity. Well, right now, my green picture is concave down, and then all of a sudden here, it changes to concave up. Now, if both of these were to have the same shift, okay, let me quick sketch this out and move it down, then what's going to happen is all the inflection points, 1, 2, 3, all the inflection points are going to happen at the same exact area. They want the equation of the line connecting the inflection points. All right, well, here's a line connecting the inflection points. This is a horizontal line that goes through negative 3. And the equation of a line that's horizontal and goes through negative 3 looks just like that. And if you're thinking, that's kind of like the midpoint, isn't it? Or the midline, I'm sorry. That's kind of like the midline, isn't it? Yeah, it kind of is. It kind of is. And I think that's what the question they were asking is supposed to be. And so I just kind of
did a little deeper dive into it. But yeah, that's what you get. It's kind of like the midline. If sine of g of x equals x and g of sine of x equals x, evaluate g of root 3 over 2. Now, this is 3.9, which is all about inverses. What this guy is saying right here is if sine of g of x and g of sine of x both equal x, that means these are inverses. So what it's asking me to do is to find g of root 3 over 2. So sine x is equal to root 3 over 2 because g of blah, evaluate g of blah, set them equal to each other. So sine of x is going to equal root 3 over 2. And you might be wondering, whoa, buddy, you sure left a lot of space there. I sure did. Because my job is to evaluate this guy, which means solve for x. Okay, so in order to get rid of that sign, I'm going to inverse sine from both sides. Inverse sine from both sides. That crosses out, and you're left with x equals the inverse sine of root 3 over 2. Now, let's remind ourselves what sine means. Sine is the y value of a coordinate. So usually I give you something like the sine of some angle is going to equal root 3 over 2. Well, that's exactly what I'm doing. I'm going to find the angle that gives me root 3 over 2. So sine is positive in the first quadrant for the both of them. So I'm going to deal with first quadrant only stuff. Okay, this doesn't ask me to do with other stuff, so I'm just going to deal with first quadrant only stuff. Okay, sine of x if I'm dealing with unit circle thoughts, or sine of whatever if I'm dealing with unit circle thoughts, is going to be a y value. Okay, so which of these three dots gives me the y value of root 3 over 2? You do. Okay, and so that's the third dot of quadrant 1. Which means this angle is pi over 3. So the inverse sine of root 3 over 2 is basically saying, hey, the sine of what angle is going to give you root 3 over 2? Well, the sine of pi over 3 is going to give you root 3 over 2. So that's what we're going to do. That's how we're going to solve it. Now, there's other problems that might ask you to go a little bit further than this, but we're not quite there yet. Right now, we're just focusing on quadrant 1, so we're going to answer it like that. Given that the domain of the sine function is restricted to negative pi over 2 and pi over 2, in order to define its inverse function, okay, so basically it's just reminding you, hey, by the way, sine looks like this. If you make the sounds, it makes it easier, right? And it's telling you in order for this to be a sine function, or in order for the inverse to exist, we have to cut you off at pi over 2 and negative pi over 2. Okay. Now, keep in mind, by the way, keep in mind what this is supposed to look like is its inverse is basically a mirror image that flips this sideways, okay, in order to find a central. What is the range of arc sine x? Now, arc sine is just fancy talk for sine inverse. Don't lose sleep over it. Arc sine is fancy talk for sine inverse. Now, I'm doing a bit too much. I just wanted to show you that, hey, if I were to take this and flip it sideways, we get this weird looking thing that looks like this. Okay, that is what we get. Now, in order to define its inverse function, what is the range of arc sine? Well, the range of an inverse is the domain of the original. And it tells you right now that the domain is that. So the domain of the original is negative pi over 2 to pi over 2, which means the range of the inverse is going to be the same exact thing. All right, so kind of weird stuff going on. But yeah, there you have it. Which of the following functions are invertible on the domain 0 pi? What does invertible mean? Invertible means you're allowed to take the inverse. Sorry, that took me a second there. You're allowed to take the inverse. To find out if something's invertible, you take the horizontal line test. And you might be thinking, is that the same as the vertical line test, but horizontal? Mm-hmm. So what we have to do is we have to graph each of these and see if each of them pass the horizontal line test. Let's graph each of them first. I'm going to put U in red. So one is going to be, and again, I only care about between 0 and pi. Regular cosine starts up here, but negative is going to start down here, so I kind of need a lot more than that. Okay. If it's 2 pi, that means the period for this one is going to be 2 pi over 2, so the period is going to be pi. So if it starts down here, it's going to repeat at pi. So starting down here is going to have it peak up here somewhere and then come back down. Okay, so that's what the graph of negative cos 2x is. Okay, let's graph sine half of x minus theta, or pi. Now, this gives me a little bit of a stretch shrink thing going here where the period is going to change. So the period is going to be 2 pi over a half, multiply the top and the bottom by 2 to get rid of that half on the bottom, and that gives me a half of 4 pi. So it stretches this out. Okay, so 2 is going to stretch it out and move it to the left pi. So normally what I do is sine starts here, but now it's going to start here at negative pi. Actually, I apologize. It starts at the right of pi. So let me do that. So let me scooch you over. It's going to start to the right of pi. So here's pi, okay? And it's going to repeat every 4 pi. So sine starts here, comes back up, dips under. So I don't need to go that far. Here's 3 pi. If it repeats every 4 pi, that means it kind of goes up and comes down at 3 pi. That's a bit too much already because I only care about going to pi. What matters here is this is going to dip under and freeze. So the important thing here for this guy, let me scooch this over. The important thing here for this guy is just that much. Okay, so when I do the horizontal line test on that guy, I'm only going to do that much. Now for 3, it's tan half of x. The period for a tangent function is slightly different. It's pi. So pi over a half means I multiply the top and the bottom by 2. So that gives me a period of 2 pi. Okay, tangent, when graphed, right, goes like this. And it has a period where basically the period is normally a pi. Now it's 2 pi. So normally for a tangent, I would have a vertical asymptote at pi over 2, and I would start here and go up. But now, right, if I start here and go up, since the period is now stretched out and doubled, I have a vertical asymptote at regular pi instead of pi over 2. Now what I need to do is apply the horizontal line test to each of these guys. So when I apply the horizontal line test to 1, it fails, which means 1 is not invertible. When I apply the horizontal line test to 2, it works. When I apply it to 3, it works. So my answers here are not going to be 1, but 2 and 3. Those are the only ones that are invertible because it passed the horizontal line test. Oh, please do like and subscribe. I need it. Given f of x equals 1/3 sine x on x being between pi over 2 and negative pi over 2, find its inverse, and then sketch the inverse, and then state the domain and range. Well, this is going to be great. Well, all right, let's find the inverse. So whenever I find the inverse, I like to pretend that f of x is y, and so that's going to equal 1/3 sine x, right? Step number 1 when finding the inverse is swap the x and the y, so 1/3 sine y. Okay, multiply both sides by 3, and that will allow the 1/3 attached to the sine to go away. Okay, so you are gone, and now we have 3x equals sine y. And if you're like, whoa, buddy, whoa, that's a lot of space for you to leave right there. I know, because the next step is to get rid of sine. And the way you're going to get rid of sine is you're going to inverse sine both sides, like that. So you inverse sine both sides. That crosses out. Okay, that gives us y equal, I'm just, flipping sides, inverse sine of 3x, so inverse sine of 3x, and then I need to write it out as f inverse of x equals the inverse sine of 3x. Now I'm going to sketch this from the point of view of f. Okay, I'm not going to act as if I have the inverse sine memorized. I kind of do, but I don't really. So let's kind of remember what sine, 1/3 sine of x looks like really quickly. Okay, really quickly. This is f of x. Okay, this peaks out at 1/3, bottoms out at negative 1/3. Okay, starts at 0, 0. It goes up and hits that 1/3 at half a pi, which so happens to be the end of my domain, which means it goes down here. Let's get rid of that. Let's try that again. It's going to go down here and bottom out, okay, at negative half a pi. So a little more curve. A little more curve. There we go. All right, that's okay. Now, when I look at this from a table point of view, okay, that's my graph. We know that an inverse is going to be the reflection of the y equals x, but let's look at it this way also. Let's look at it from a table point of view. Here's going to be my x and f of x. My key points are at negative pi over 2, I'm at negative 1/3. At 0, I'm at 0. And at positive pi over 2, I'm at positive 1/3. Now, the table of an inverse is flipped. So its inverse is going to be negative 1/3, negative pi over 2. Flip them. 0 flipped with 0 is 0, 0. And 1/3 is going to be my x value, and pi over 2 is going to be my y value. So now when I graph this, okay, when I graph this, I'm going to peak out at pi over 2, and I'm going to bottom out at negative pi over 2 down here. I'm going to go to the right 1/3 and to the left negative 1/3. And when I graph this, I have that 0, 0. I have that dot right there, poorly drawn, and that dot right there, poorly drawn. And this is going to be the action we come up with. Okay, so that is the graph of its inverse. Similar, very similar, but if you can kind of see, if I were to draw like a perfect diagonal there, this would kind of flip and that would kind of flip, and then that's kind of what's happening there. All right, now what does that do with the domain and the range? Well, here was the domain of my original problem, which means my range is going to be the domain of my original problem. Now, when I graphed my original problem, let me just write that out. Let me just write it out. When I graphed my original problem, it peaked out at 1/3 and bottomed out at negative 1/3. Okay, it peaked out at 1/3. So my range for regular f of x was negative 1/3 to regular 1/3, which means my domain of the inverse is going to be the range of the original, like that. Okay, so I approached this problem slightly differently, where instead of trying to memorize what the inverse looks like, I found the inverse and then graphed the inverse using information about the original. Well, wasn't that fun? It was. Graph g of x equals cos x on 0 pi. All right, let's do that. Let's do that right now. Let's do it in red. Cos x starts up here at 0, 1. I'm going to pi. So remember, the period of cos x is 2. So you kind of go like this. Okay, and so since 2 pi is my period, pi is where I would bottom out. And I want to go to pi. So I'm going to cross the x-axis here. I'm going to bottom out at -1. I'm going to leave that open because I'm not allowed to include it. And I'm going to try to draw a wave like that. Okay, that's my cos. Use that graph to graph G inverse as a reflection over the x equal y axis. Okay, well, I am not good at looking at this information and just trying to pretend that there is a mirror image there. That's not my thing. So this is what I'm going to do. Okay, I have 3 key points here that I'm going to try to spin around. One of my key points is 0, 1. Now, the inverse and the regular problem, when you try to take the regular problem and turn the inverse, you flip the inverse. So my 3 points that I noticed from the original problem were 0, 1, pi over 2, 0, and pi, -1. So if I were to graph the inverse in blue, I can graph the points 0, 1, 0, pi over 2. Nope. Yep. Nope. I knew something wasn't right there. 1, 0. I was supposed to flip them and I didn't. Shame on me. 0 pi over 2 and -1 pi. Okay, so let's try to do that. Do I have the space for it? Well, I'm going to force it if I don't. Pi over 4. Pi over 2 is like 1.5. So pi over 4, I believe, is like 0.7 something. So we'll say 1 is right there. So 1, 0 is going to live right there. 0 pi over 2. Pi is 3.14. So half of a pi is like 1.6-ish. So we'll put you like right around here. Okay, and -1 pi. -1 is going to be like right there. So -1 pi is going to be up here, and that's technically going to be a circle. So you will look like you. If I knew how to draw, which I don't. So we'll do a little scribbly thing so it looks okay. But there you have it. That's what my inverse cosine is going to look like. And I used my mirror image and the fact that these guys flip-flop as my guide. You know, Jimmy the Cricket says use your conscience be your guide, but inverses do the job too. Hee hee, like and subscribe. What value of d would allow g of x equals inverse tangent of x plus d match the graph? Well, let's just say that you don't even know what the inverse tangent looks like. Okay, I know that regular tangent looks like this and goes through the origin. So that's the point 0, 0. Now the inverse is going to also be 0, 0 because I flip-flop them. So according to this picture, regular old inverse tangent is probably going to look something like this where it crosses over 0, 0. Well, now I'm going to take that thing that's supposed to cross over 0, 0 and shift it down a few units. So how many units am I shifting it down? 1, 2, 3, 4. So if d was equal to -4, then my inverse tangent would match that graph down there. And there you have it. For this one, all I'm doing is finding the inverse of f of x equals 4 sine pi x. I'm not going to worry about domain restrictions. I'm not going to graph. I'm just finding the inverse. Whenever you find the inverse, what I like to do is f of x seems to throw my ADHD brain off, so I'm going to use y instead of f of x. Step number 1 is you flip-flop the x and the y. So x equals 4 sine pi y, or y pi, or pi y, or y pi. Now, I have to get y all by itself. First things first, let's get rid of that 4 by dividing everything by 4. So divide by 4, and now I have 4 below x equals sine of pi y. Now, if you're looking at this and saying, boy, sir, you sure left a lot of space there. I know, I did, and I did it on purpose. And here's the reason why I did it on purpose. I have to inverse sine both sides to get rid of the sign on the right. So if I inverse sine both sides, now I have inverse sine of x over 4 equals, these guys cancel each other out, pi y. To get y all by itself, let's divide everything by pi, or better yet, multiply everything by 1 over pi. That'll make the left side look a lot more pleasant. Multiply everything by 1 over pi, and that leaves me with 1 over pi inverse sine of x over 4 equals y. Now, if we flip-flop things, so now that I have 1 over pi inverse sine of x over 4, instead of writing y on the left, I'm going to write what it's supposed to look like when finding the inverse. So the inverse of f of x is 1 over pi sine inverse of x over 4. And there you have it. Find the inverse of g of t equals 1/3 sine 2t minus pi over 2 plus 5. What I like to do is g of t throws me off. I'm going to replace g of t with y and write it out like this. Is this a necessary step? Nope. But it helps me out because the extra parentheses has a tendency to throw my ADHD brain off, and I can't do it. Step number 1 is replace the x and the y. In my case, the y and the t. So t is now going to equal negative 1/3 sine 2y minus pi over 2 plus 5. I have to get sine all by itself. There's a negative 1/3 in the way. There's a 5 in the way. There's a 2 in the way. There's a negative pi over 2 in the way. Let's get rid of that 5 first by subtracting 5 from both sides. T minus 5 equals negative 1/3 sine 2y minus pi over 2. Now I'm going to get rid of that negative 1/3. I'm going to multiply both sides by negative 3 because it's the reciprocal. So I'm going to multiply both sides by negative 3. On the left side, I have distributive property. Negative 3t plus 15. These guys cancel out. It's going to equal sine 2y minus pi over 2. And if you're like, whoa, buddy, you left all that space there. I know. It's because my next step is to inverse sine both sides, and that gets rid of the sine. So inverse sine both sides cancels out the sine there. And what I'm left with, and let's move it up here, is the inverse sine of negative 3t plus 15 equals 2y minus pi over 2. Okay, in order to get y all by itself, I have to add pi over 2 to both sides. So let's add pi over 2. Let's add pi over 2, which doesn't combine to anything here. So that leaves me with pi over 2 plus the inverse sine of negative 3t plus 15 equals 2y. Last step is to divide everything by 2. I'm actually going to multiply everything by a half because I think that'll just make it look a little bit more pleasant. So I'm going to multiply everything by a half because that allows me to cancel these guys out. So big distributive property times a half is going to give me half of pi over 2, which is pi over 4, plus half of the inverse sine of negative 3t plus 15. And that equals y. So last step is I'm going to swap sides, And I'm going to move that pi over 4 plus half of the inverse sine of negative 3t plus 15 and move the y to the left. But remember that it used to be g of t, so now I'm going to call it the inverse of g of t. Very, very, very busy problem. Very busy problem indeed. Find theta. Well, we have ourselves some right triangle trigonometry, boys and girls. This is a radius. This is a y value. Now, which one of my sine, cosine, tangent guys gets me the radius and the y value? Well, that would be sine, of course. So sine theta would be the y over r. Okay, so the y is 6. So sine theta is 6. The r is 12, which last time I checked simplifies out to a half. Now, what this is asking me is, all right, the sine of what angle gets me a half? Well, remember, sine is a y value. So if I'm thinking, all right, well, what positive y value gets me a half if I was thinking unit circle thoughts? The dot right in the middle. The dot right in the middle doesn't. I'm sorry, just kidding. Not the dot right in the middle. The first dot. The first dot. Ooh, all of that. The first dot is going to get me the y value of a half. And that first dot is represented by pi over 6. So if I were to inverse sine both sides, right? I'm again asking you what theta, if I were to take the sine of it, would get me a half? Well, pi over 6. And not pi over 4 like I originally thought. It was a close one, but I pulled it through. Find the exact value of the expression given the domain restrictions. All right, well, look at those domain restrictions right there. It looks like I'm allowed to go to 1 and -1 or somewhere around there. I don't know. Find the exact value of the expression. Well, the inverse sine of -1/2 is basically asking you what angle, if I were to take the sine of that angle, gets me 1/2, or in this case, -1/2. Well, if I were to take the sine of pi over 6, that gets me 1/2. But I don't have that. This is negative. So -1/2 is going to give me a negative answer here because it's going to be somewhere over here. So simply put, negative pi over 6 is going to be my guy, because if I were to take the sine of a negative number, you're basically asking, all right, well, I want the negative y value that gets me -1/2. So in this case, it's going to be negative pi over 6. Now, normally, maybe we would write out pi over 6 by adding 2 pi or something along those lines. But given the restrictions, I'm only allowed to keep it between -1 and 1. And my y values are only supposed to be in between what appears to be pi and negative pi. So I'm not allowed to do stuff like adding 2 pi, because then that takes it outside of the restrictions. You see? The end. Solve the equation for theta on the interval 0 to pi. 1/2 equals cos theta. I'm just going to rewrite this like this, and you might be wondering, why? Why all that space, sir? Well, I have to get theta all by itself, which means I have to get rid of cosine. How do you get rid of cosine? You don't divide cosine, you inverse cosine both sides. Inverse cosine both sides. That's why I gave myself that space. Now I can cross this out, and flipping things around, you can now say that theta equals the inverse cosine of a half. Now, basically what you're doing is you're asking yourself, cosine of what angle gives me a half? Well, first things first, cosine is the x value on the unit circle. So where on the unit circle is the x value going to be positive? In these two quadrants right here, quadrants 1 and quadrant 4. Now, where is my x value 1/2? Well, my x value is 1/2 here, which means it's also going to be corresponding here. This is the third dot on the unit circle where x is 1/2. So it would be like 1/2, who cares, or 3/2. And this would be 1/2, negative root 3/2, but, who cares? Now, most importantly, again, my job is to find out what equation, or better yet, what angle, would give me these numbers. Well, u would be pi/3, because u would be the third point in my unit circle, and u would be like the negative pi/3, also known as 5 pi/3. Those guys fall within the boundaries of 0 and 2 pi, so theta is going to equal pi/3 and 5 pi/3. And that's your answer. Find all solutions 1/2 times sine theta equals negative root 3/4. Now I have to get theta all by itself, so let's start out by getting rid of that half and multiply both sides by 2. So multiply u by 2, multiply u by 2, that crosses out. Sine theta equals 2/4 simplifies out to 1/2. So this ends up being negative root 3/2. And you might be like, whoa, brother, why all that space right there? Well, the next step is to get sine all by itself, which means I have to get theta all by itself, which means I have to get rid of sine. And the way you get rid of sine is you inverse sine both sides, like so. That crosses out, and theta now equals the inverse sine of negative root 3/2. So basically what this question is asking is what angle, or sine better yet, of what angle gets me negative root 3/2. So now we have to think unit circle thoughts. Sine in the unit circle is a y value, and I'm taking the inverse sine of a negative y value. Where is y negative on the unit circle? Well, underneath the x-axis. So sine is negative underneath the x-axis down here. Now, if I were to put dot, 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 and dot, 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 like so, and do all the things and try to find out where sine, or y, is negative root 3/2, well, that will happen right here. I would get 1/2. Not that that's important, negative 1/2 technically, and negative root 3/2, which corresponds, that's this point, by the way, which also corresponds to this point, by the way, as well. So whatever x value, negative root 3/2. Okay, this is pi, which means u are going to be 1/3 between pi and 2 pi, which is 4/3 pi. So let me say that, 4/3 pi, or 4 pi/3, however you want to word it out, which means this is going to be 5 pi/3. So theta is going to equal 4 pi/3 and 5 pi/3. Ooh, however, I have no interval here saying that those are going to be my only answers. So I need to find all of the solutions if 4 pi/3 is a possible one and 5 pi/3 is a possible one. Well, what are all of my solutions? Well, basically this point and every plus 2 pi, every plus 2 pi, or every minus 2 pi, minus 2 pi. So the way I will word this out at the very bottom is I will say theta is going to equal 4 pi/3, but I'm going to add 2 pi a bunch of times. So I'll say plus 2k pi. What's k? K is any integer. So if k was 0, I would add 4 pi/3. If k was 1, I would add 2 pi. Or if k was negative 1, I'd subtract 2 pi, which basically just means every time I spin around the circle. So if I do that for 4 pi over 3, and you noticed all that space over there, I'm going to have to do that with every 5 pi over 3, which means every time I spin it around the circle normally, or if I subtract 2 pi, that's going to do it too. So 5 pi over 3 plus 2k pi as well. Okay? And that'll give me all possible solutions for that equation right there. Wasn't that fun? Find all the solutions for 2/5 times cos theta equals root 2 over 5. I have to get theta all by itself, so let's start out by multiplying the bottom and the top, or better yet, multiplying both sides by 5 over 2. Let's just do the reciprocal, probably a whole lot easier. That way you cancel out, cos theta is all alone. You guys cancel out, and that gives me root 2 over 2. And you're like, whoa, buddy, all that space, why? Well, the next step is to get theta all by itself. And to get theta all by itself, we inverse cosine both sides, which is why I needed that space. So now theta is the inverse cosine of root 2 over 2. Now, what this is asking is cosine of what angle gives me root 2 over 2. So now I need to think unit circle thoughts. So unit circle thoughts, cosine is an x value. In this case, cosine is a positive x value because this is a positive number. So when I take the cosine of whatever angle I come up with, I'm going to end up with a positive number. So x is positive in quadrant 1 and quadrant 4. So let me draw a unit circle there. Which point of my triple point thing here and here is going to give me an x value of root 2 over 2? Well, right in the middle. And right in the middle as it corresponds over here. Now, this is 1/4 of its way from 0 to 2 pi, which means, 0 to regular pi. Regular pi, boy, would that change things. Which means 1/4 of a pi is pi over 4. So theta is going to be pi over 4, which means you are going to be negative pi over 4. If I knew how to draw the line correctly and drew it to the right spot, you would be negative pi over 4, which is taken away from 2 pi, which is 7 pi. That was me trying to erase. Oh, sorry. Please like and subscribe. Which is going to be 7 pi over 3. So that's my other option. 7 pi over 4. Now my job is to find all the solutions, which means I could get pi over 4. And I could spin it around either direction and get plus 2 pi, and then plus 2 pi again, or minus 2 pi, or minus 2 pi again. So how do we write all of that out? Well, we'll say that theta is going to be x over 4, or pi over 4, and every time I added 2 pi. So I will add plus 2k pi. And you might be like, whoa, 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 what's k? K is any integer. Okay. So if I were to add 0, I'd get pi over 4. Or if I were to make k 1, it would be plus 2 pi. Or if I were to make k negative 1, minus 2 pi, so on and so forth. So if I do that to pi over 4, I'm going to have to do that to 7 pi over 4 as well. So 7 pi over 4 plus 2k pi, where k represents any integer. So a little bit of artistic slip-ups over here. But you know what? In the end, it doesn't even matter. Lincoln Park. Like and subscribe. Find all the solutions for negative 15 plus root 3 all over 3 equals negative 5 plus tangent theta plus 3 pi over 4. Ugh. First things first, let's get rid of that 5, that negative 5, and we'll do so by adding 5 to both sides. Now, if I'm going to add 5 to something over 3, I'm going to turn this into 15 over 3 because that's what 5 is when I multiply the top and the bottom by 3. That allows these guys to cancel out. And you're left with root 3 over 3 equals tangent theta plus 3 pi over 4. Now, how do I get rid of that tangent so I can open up that whole parentheses there? Inverse tangent, of course. So I'm going to inverse tangent root 3 over 3. That allows that to cross out. Now, here's the thing that I have to be careful of. I am asking you what angle gives me root 3 over 3 if I take the tangent of it. So where is tangent going to give me a positive slope? Well, tangent is going to give me a positive slope because remember, tangent gives me slope of a ray. When x over y is positive, or y over x is positive, and y over x is negative and negative, which makes u positive. So quadrant 3 seems to do it. Okay, now the tangent, the inverse tangent of root 3 over 3 in the positive axis is going to be root pi, irregular pi over 6. But also, and this is my and, not plus, also in the third quadrant, it's going to be 7 pi over 6. And that's going to equal theta plus 3 pi over 4. Now, you might be thinking, I think he's doing a bit too much. And you're kind of right. You're kind of right. But let's just do it anyway. We now have two equations that we have to solve for. We have pi over 6 equals theta plus 3 pi over 4. And we have 7 pi over 6 equals theta plus 3 pi over 4. Okay, this is a learning process. This is not me just kind of, let's just blindly do the problem. Let me do the problem, realize that I did too much, and we'll explain the mistake in a minute. Let's subtract 3 pi over 4. So that would basically be like 2 pi over 12 minus 9 pi over 4. So negative 7 pi over 12 is going to equal theta. And if I do the same thing over here, minus 3 pi over 4 minus 3 pi over 4, that would basically be like me saying, what, 14 pi over 12 minus 9 pi over 2. So 5 pi over 12. That's going to equal theta. Here's the thing with tangent. And this is where I'm now going to realize, I did too much. The period of tangent isn't 2 pi like it is for sine and cosine. It's regular pi. What's negative 7 pi over 12 plus pi? You guys are the same exact thing. I did too much, which means the main guy that I care about is either one of these. Now, hold on, time out. I have no interval. I have no interval whatsoever. So what I need to say at the very end here is theta is going to be like negative 7 pi over 12, or 5 pi over 12, or plus another pi, or plus another pi. So I'll pick one of these, 5 pi over 12 plus k pi. What this does is if I let k be any integer, if I said k is 0, then I get 5 pi over 12. If I said k is negative 1, then that means minus pi, which is negative 7 pi over 12. Or if I add 2 pi, or if I add 8 pi, any of these guys will work. So kind of tricky, kind of weird, lots of fun. You're studying ocean waves with this terrible, terrible, terrible equation right there. Oh, thank you. It's a calculator problem. At what time t will the ocean wave reach a height of 3 meters? So what we're going to do is we're going to graph this guy in our graphing calculator. We're also going to graph where the height is 3 and find out where these two guys intersect. So let's run to the calculator and see what happens. So you're studying ocean waves, huh? Well, let's type out this weird-looking function. It's a sine function, so 2, there's my sine. I always get paranoid with fractions, so I'm going to do parentheses pi over 4. So pi is u is pi, divided by 4, like that. Now we can close it. Instead of t, we're going to use x minus another fraction, so another parentheses pi. Pi is u is pi. Divided by 3, close it again, plus 1. Now, let's get a picture of this. I know we're not done, but let me zoom trig by hitting zoom 7, and that gets me kind of my sine wave right there. At what time t will the ocean wave reach a height of 3 meters? Well, first things first, this is real life stuff, right? So I don't care about negative x values. I don't. So at some point, there's my picture. I'm going to hit 3 meters. So here's 1, 2, 3. At some point, I'm going to hit 3 meters. Maybe it looks like probably. So why don't I find out what that time is by going to y equals 3 and then finding out where these two guys intersect. So it's going to intersect somewhere around here. Second calc will let me find the point of intersection. So I'm going to hit second calc 5. My first curve, I'm going to make sure I'm to the left of what looks to be the intersection point. Knowing what I know about altitude and vertical shift, it looks like it's literally going to peak out at 3, because it does. So I'm going to make sure I'm to the right of 3, hit enter, and when I hit enter again, it gives me the intersection point of 3.333333333. So I'll say 3 1/3, I guess. Well, we got ourselves a nice little 3 1/3. So since this is pre-calc, we'll do 3.333. Nothing. No, they don't tell us. Well, thanks, ChatGPT. You blew it. You blew it. So t equals 3 1/3. Fun stuff. A person whose eyes are 5.2 feet from the ground stands at a distance of 21.45 feet from the base of a tower. The person looks upward at the top of the tower with an angle of elevation of 0.1/3 pi radians. What is the height of the tower? Let's draw this out. This is where you're going to really see my amazing artistic skills. There's our guy. He is looking at a tower. We don't know how tall the tower is. That's kind of the point. All right, so here is a tower. What we do know is this guy is 5.2 feet from the ground. Okay, he's looking up at an angle of elevation of 0.13 pi radians. We know he's 21.45 feet from the base of the tower. So you're 21.45. And my job is to find the height of the tower. So we'll call the height of the tower y because this is pre-calculus and up and down uses y. So what I need to do is I need to figure out which trig function, SOHCAHTOA, is going to give us the adjacent and the opposite side. Well, tangent does that. So we would say that the tangent of our angle, 0.13 pi, is going to equal y over 21.45. Now, my job is to find y, but that's not going to be it. But I'll get to that in a second. If I want to try to throw all of this into my calculator all at once, which is what I'm going to do, I'm going to multiply both sides by 21.45. I'm going to multiply both sides by 21.45. And so in my calculator, I now know that y is equal to 21.45 tangent 0.13 pi. However, that's not the height of the whole tower. The height of the whole tower is done by calculating 21.45 tangent 0.13 pi. But then on top of that, the fact that this guy is 5.2 feet off the ground. So I'm going to add 5.2 to that. And that will give me the height of the tower if I type it all in one foul swoop. So let's do that. All right, so we did all the heavy lifting on the Google slide video part thing, whatever you want to call it. So now all we have to do is just type that out. 21.45 tangent of 0.13 pi. Pi is u. Close the parentheses. And that gives us the height of the tower without the person's height. So let's add the person's height to it. And that gets us 14.4822. So it's a small tower, but it didn't say it had to be big. It's a small tower. So not a big tower here. You got 14 0.482 feet. So, yeah, that's what you get. Small tower. The population of rabbits is modeled by the equation R of t equals 182 plus 175 sine 2 pi t over 365, where t is measured in days. On what intervals is the population increasing within the first 365 days? So a very basic view of this problem is this is sine with no shifts. All right, now what's going to happen? I'm sorry, there is a shift. There's a vertical shift. Okay, so I don't know exactly what's going to happen and where it's going to happen. What I do know is its sine, it's going to go like this, and it's going to go like that, and yada, yada, yada. And at some point, I'm going to have an area where it's increasing, and then probably an area where it's increasing again, and maybe it repeats itself. I don't know. But what I need to do is I need to find out where it stops increasing. And it stops increasing at a maximum, and then is decreasing, and then it starts increasing at a minimum. And maybe it happens again, and maybe it happens again. I don't know. But what I need to do is I need to graph this guy in a graphing calculator, find all necessary maximums and minimums, because those maximums and minimums tell me where this guy is increasing. And I have to make sure I follow the rules of 365 days. So let's see what happens. All right, so we're talking about rabbits. So y is going to equal 182, just like that one band who blinks a lot, plus 1, that's a 7, 175 sine, let me double the parentheses. I always get very paranoid. 2 pi r, t, which is going to be my x. So we'll put that in parentheses, divide that by 365. That's days in a year. We'll close that, and that should do it. So let's zoom trig to get a better viewpoint of what's going on. And I get nothing. And if you're wondering, well, why do you get nothing? Well, because if I'm adding 182, that's a vertical shift of 182. That's a lot. So let's go to my window, and let's start out with my y min of, well, first off, my amplitude is huge. So let's keep the y min at 0. If I'm dealing with numbers like 182 and 175, let's attempt 300, and that might do the job. All right. Now, clearly, this ain't going to do it. Why? Well, it also mentions numbers like what's happening within the first 365 days, and it looks like I don't have 365 days. So let me make my window go from, I don't need any negatives because negatives mean negative time, and that doesn't make sense. So let me go to I'm going to the wrong thing. My x max, let's do -1. And let's do my y max at 370, just, to go a little extra. Just to go a little extra. All right, so let's bump our window, our y max to 400. And that should hopefully give me what I need to see. Yes. Now, I care about when this is increasing. So it looks like it's increasing. And I said this in the part beforehand. I need to find out from here to its max where it's increasing. Now, clearly it's increasing, and it stops increasing at the max. So I have to find the max right here. Now, it's going to decrease until the min and starts increasing until the very end. So once I find out my maximum value and my minimum value, I'm good to go. So second trace maximum will help me find my max value. So let me scroll to the left until I go to the left of my maximum. There. Enter. Let me move to the right of my maximum. Enter. Guess. Enter. And it's going to tell me that the maximum happens at 91.2599. So 91.260 is going to be a maximum value. Just writing that out so I can write it back down. All right, let's find my minimum value. Same idea, but min. Second calc. Minimum is 3. So let's move to the right a bit, go to the left of my minimum, move to the right some more, hit enter on that, hit enter on that, and my minimum is a beautiful 273.75. All right, so my maximum number was 91.260. My minimum number was 273.75. And this picture that I drew out ended up being pretty nice. So I'm, a little pat on the back for me. Now, the way I write that out in interval notation is it begins increasing right away. So I will include 0. And it goes all the way to 91.260, but I won't include it because that number technically goes on forever. Then I've got union. Now it's decreasing for a while, and it picks back up again at 273.75 exactly, and then goes all the way up until 365 days, including. All right, so those are my intervals where these guys are increasing. Fun stuff. Rabbits. Verify the identity 1 over sine x cotangent x is the same thing as 1 over cosine x. So I need to make this guy the same as 1 over cosine x. Well, what do I know? Sine is sine, can't do much about it. But what I do know is cotangent is cosine over sine. So let me write that out. Cosine over sine. Oh, look. A sine up here and a sine down there. Let's cross them out. And when I cross them out, I'm left with 1 over cosine x, which is what I want to find. I did it. Consider the sinusoidal function. Find the x values of the minimum values of the function on the interval 0 and 4 pi. So this is a cosine, but it's a mess. So, we're going to have ourselves some kind of periodic function. I care about the x values where I have my maximum. So whatever the picture looks like, and using the fact that this is only between 0 and 4 pi, I'm going to try to find the maximum values between those numbers, 0 and 4 pi, in my graphing calculator. So let's see what happens. Well, this one's a doozy. Let's just get right to it. Y equals 4.651 cosine 0.833. There's my x minus 1.239, close parentheses, plus 4.101. This is my favorite amount of Dalmatians. Now, what I'm supposed to do is I'm supposed to find the x values of the maximum value or values on the interval 0 to 4 pi. Now, looking at this, my numbers are gross, but they're not huge. And I'm looking at the amplitude rather, and the phase shift. The phase shift is around the 4 range, and the amplitude is also around the 4 range. So before I do much, let me zoom trig and find out that picture is probably not going to be good enough. See? And now it gives me an idea. I need to find my maximum value. So it looks like my window, I'm probably safe for -1. Probably safe there. Not that I care because I need the max value. And let's go up to 10 for my y max. And hit I'm not going to hit graph yet. What I'm also going to do is I'm going to make sure that my interval is where it needs to be. So let me set it at -1. This is supposed to be from 0 to 4 pi. So let me go from -1 to 5 pi. Okay? Now I can graph. Much better, much better, much better. So between 0 and 4 pi, I have 2 maximums, it looks like. 2 maximum values. So let's find them. Let's find the maximum the first time. So let me go to second trace and hit 4 for maximum. Let me go to the left. Okay. Enter. Enter. And that gives me an x value of 1.487. Okay, so that is one of the x values that gives me the maximum given the intervals 0 and 4 pi, 1.487. Now, the other one is going to be done by doing the same exact thing. Second calc maximum. Let's move to the left. Move to the left some more. Guess always hit enter, and we're looking at 9.0392, so 9.039. Those are my two guys. So I had two, and those two x values were 1.487 and 9.039. Good job, everybody. Thanks for watching. Graph f of x equals secant x. Now, this is the very first time we're graphing secant, and what I want to do is I want to break things down as friendly as humanly possible. Secant is 1 over cosine. So the way you graph a secant is you use cosine as your rough draft. Okay, so what cosine does, gentle reminders for cosine, is cosine has a period of 2 pi. It starts out at 1, 0, and it repeats itself every 2 pi, and so on and so forth. So let's graph 1 over cos x as our rough draft. All right, so looks like this. What do I have? 2 pi, so it's going to cross here. It's going to bottom out here. It's going to cross here. It's going to peak out here. So drawing a rough draft, this happens. Similarly over here, drawing a rough draft, this happens. Good. Now this is basically like my guide. Okay, this is my guide to draw secant because secant is 1 over cosine x. If you have an x in the denominator, that's no good because what that tells you is at some point you should expect vertical asymptotes whenever the bottom is going to equal 0. Now, when is regular cosine x equal to 0? Well, let's look down here. Cosine x, the rough draft, equals 0 whenever it crosses the x-axis. Now, what that means for us is that gives us vertical asymptotes for secant x. We're going to have a vertical asymptote wherever cosine x equals 0. So anytime my cosine x crosses the x-axis, my regular equation is going to have a vertical asymptote. So I'm going to draw vertical asymptotes wherever my cosine function crosses the x-axis, like so. Now, obviously, I haven't begun drawing my secant, but I'm getting there. Okay, one more step and I'm going to get there. All right, I know that secant looks like this, where you kind of have these parabola-looking things and they kind of take turns going up and down and up and down and up and down. Well, where do they begin? Well, first off, I know that secant x is going to equal specific things when cosine of x equals something like 1. For example, when cosine x equals 1, secant x equals 1. Okay, so if I could figure out where cosine x equals 1, that allows me to place dots on 1 for secant x. So it equals 1 here, it equals 1 here, and it equals 1 here. Similarly, if cosine x was negative 1, secant x would be negative 1, which allows me to put dots here and dots here. Now I have enough information to draw my actual graph, which is what I'm going to do now. Again, secant kind of follows this parabola-looking thing where it's concave up, then concave down, then concave up, then concave down. So I'm going to try to draw that. Concave up, now concave down. Concave up, now concave down. And last but not least, concave up. So again, what I did is I rewrote secant as 1 over cosine x, and I allowed that to be like my rough draft as to where things were. Now I know what's going to happen. Now I know wherever this 1 over cosine rough draft, wherever this cosine peaks out is where my secant begins. Wherever it crosses the x-axis is where I have a vertical asymptote. So as I do more problems and I start adding amplitude and phase shifts and stuff like that, I now know what this is going to look like. Okay? Secant x, pretty important and fun. All right, let's graph g of x equals cosecant x. Now, whenever I graph cosecant or secant or cotangent, I like to view it from the point of view of its reciprocal. So cosecant is 1 over sine x. And so what I'm going to do is I'm going to graph sine x as kind of like my guide to graph cosecant x. So what do we know about sine x? Well, it's regular sine x starts at 0, 0. It peaks out at 1. It bottoms out at -1, period of 2 pi. So let's graph that out. Okay, 0, and then it peaks out here, and then it re-hits, and then it bottoms out, and then repeats. And then the reverse is also going to be true, so let's draw that out. Okay, sine. Now, this is, again, like a rough draft or a guide, if you will. Not even a rough draft, but more of a guide. Because if you saw my video on secant, what's going to happen is very similar stuff. Okay, very similar stuff. Now, what's very important that I understand here is I have a x in the denominator, which means there's going to be a point, literally, and several of them where sine of x is going to equal 0. Well, whenever sine of x equals 0, that means cosecant has a vertical asymptote. Well, that just means that sine x is 0 at these moments right here where it crosses the x-axis. So you are a vertical asymptote. You are a vertical asymptote because x equals 0. Because sine x equals 0 at these moments. So vertical asymptotes here where it crosses the x-axis, and vertical asymptote here where it crosses the x-axis. Now what I have, and again, very similar to secant, is I'm rotating what appears to be like parabolas. Where do these parabolas start? Well, right here. Okay. Why do they start right there? Because it's following the pattern of its reciprocal. So this is basically going to look like it has a parabola here. Okay. This is going to kind of go downward. This is going to go upward. And this is going to go downward like so. Okay? So if I was a better artist, this would look a lot prettier. But I'll give myself a little pat on the back. This ain't so bad. Graph h of x equals cotangent x. All right, cotangent x is very lovely to graph compared to cosecant and secant because it's kind of like a flipped reverse version of tangent. Now, what do we know about tangent? Tangent goes through 0, 0, looks like this, has a period of pi. So, this happens at half a pi, this happens at negative half a pi, so on and so forth. Cotangent is very, very, very similar. With cotangent, though, we have vertical asymptotes, not at the half pi's, but at the regular pi's. So I will put vertical asymptote at every k pi where k is an integer. Okay. In this case, cotangent is going to look like this. And the period for this is also regular pi. So why don't I do this? Why don't I write out my vertical asymptotes? And if you're wondering, why are the vertical asymptotes here? Cotangent can be written out as sine over cosine. Sorry, I'm trying to draw dots and speak at the same time. So whenever cosine, since it's sine over cosine, is equal to 0, that's where I'm going to have my vertical asymptotes. All right. So here you have it. Now, this is going to be Goes right there, goes right there, goes right there, goes right there. And this is going to look like the flipped version of tangent. Okay, so just kind of try to draw that out. Ugh, I'm so bad at these. So kind of like these weird things that change its concavity halfway through. Yeah. All right. So cotangent, a lot friendlier to draw than cosecant and secant. Not friendly, but friendlier. Friendlier. And that's all we can ask for. Graph f of x equals 2 cosecant pi x. All right, this is how I graph my reciprocal functions. I kind of view this from a standpoint that this is basically the same as 2, 1 over sine pi x, right? And so what I need to do is I need to graph this guy and let this guy be my guide. Now, what do we know about this? Well, amplitude is 2, so that helps. Okay, amplitude is 2. And also, there is a pi in front of x, which means my frequency is pi. And for sine functions, if your frequency is whatever, you find your period by doing 2 pi over that whatever. And my whatever is pi, so cross out the pi's, and my period is 2. So what I'm going to do is I'm going to draw, this is a very rough sketch, so, you know, don't cling on accuracy, especially since I can't draw lines with this thing. My period is 2, so not pi's, which is why I didn't get some kind of trig graph. So I'll go 1, 2, 3, 4. I'll go 1, 2, 3, 4. Okay. Now, drawing out, oh, you know what? I also need these. These will help. 1, 2, 3, 1, 2, 3. All right. So, drawing out my rough draft of what this looks like. Okay, I have an amplitude of 2. I have a sine whose period is 2. So I start here. Everything repeats. Everything repeats. So I go up to 2, come back down, go down to -2, come back up. Go up to 2, come back down, go down to -2, come back up, and vice versa. So go down to -2, up to regular 2, -2, regular 2, boom. Okay, so this is like my rough sketch. Now, while I'm drawing this out, this is going to be my guide for what this cosecant function is going to look like. Anytime my graph goes through, my sine graph, my rough graph, goes through the x-axis, that means it hits 0 in the denominator for a cosecant. And when 0 is in the denominator for your cosecant, well, that, boys and girls, is a vertical asymptote. Vertical asymptote, vertical asymptote. So as I draw all these vertical asymptotes, including you, okay, the next thing that I'm going to consider is the fact that this is a cosecant function which looks like alternating parabolas. Okay, cosecant functions look like this. Usually it starts at 1 and -1, but since the amplitude is 2, these guys are going to start at 2 and -2. So my final graph is going to look something like this. Okay, alternating parabolas looking things. Okay. So again, you know, I'm not going to win any awards for the prettiest picture ever, but I allowed the sine, which is in green, to be my guide, which gave me vertical asymptotes, which gave me the final graph at the end of the day. So, not the prettiest, but I did it. Give an equation for the vertical asymptotes of 1 over secant x minus pi over 2 in parentheses. Vertical asymptotes exist when the denominator of a function is equal to 0. Now, I know what secant is. Secant is the same exact thing, and I can rewrite this out as this. Secant is the exact same thing as, in this case, 1 over 2 cosine x minus half over 2. So I care about when the denominator is equal to 0. When a denominator is equal to 0, that gives me the vertical asymptote. So I'm going to take this equation here in red, and I'm going to solve it for x. Dividing both sides by 2 gets rid of the 2 in front of cosine, which does absolutely nothing to that 0 right there. It is still 0, which makes sense because this implies amplitude, and amplitude has no effect on where vertical asymptotes are. Let's leave some space. Why? Because my next step is to inverse cos both sides. Boy, I left the space on the wrong side. Inverse cos both sides, like this. Now, what this does is I now have two guys that I have to deal with, because if I'm dealing with 1 over secant, and here I don't have two guys. I basically am just, I'm dealing with all possible answers. So if I'm thinking, unit circle thoughts, okay, if I'm thinking unit circle thoughts, I know that the inverse cosine of 0 means I care about when an x value is 0. And an x value is 0 exists at 2 spots when I'm dealing with the unit circle, okay? Here, not here, but here and here. And those 2 spots, as far as radians go, are going to be pi over 2 and 3 pi over 2. So this cancels out. X minus pi over 2 is going to equal the inverse cosine of 0, which is pi over 2. And also, x minus pi over 2 equals 3 pi over 2, like so. If I add pi over 2 to both sides, that gets me just a pi. And if I add pi over 2 to both sides, that gets me 2 pi. Now, this is going to be, my vertical asymptotes are going to repeat. And to make life easier, usually what I would do is I would add plus 2k pi to both of these. But wait a minute, I don't need to do that, because if I'm going to have pi and 2 pi, that would imply 3 pi and then 4 pi and stuff like that. So basically it's all the pi's. So my final answer is, if my answer is going to be pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, it's going to be x equals k pi, where k is an integer. Okay, so there you have it. Find the range of f of x equals 3 secant parentheses 2 parentheses x minus pi over 2, close it, minus 2. This is a nightmare if we let it be, but I'm not going to let it be. Here's the thing. I'm not graphing this. All I need to do is find the range. So what I'm going to do is compare this to its counterpart, which is the same thing as saying like 3, 1 over cosine, blah, 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 blah. And then let's erase a little bit, and then minus 2 at the end. Now, why am I doing all this blah, 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 blah stuff? I know if I were to graph this guy right here, okay, I'm caring about 2 things. Thing number 1 is the amplitude, okay, and thing number 2 is the vertical shift. Okay, me moving left or right or changing the period is not going to change my range. However, me changing the height of my function, or me changing where the height begins at the function, gives me my graph. So if I were to look at this very rough sketch, okay, and I'm comparing 3 cosine -2 as my rough draft, what I'm going to do is I'm going to draw that out as my rough draft and not be too much about it. Okay, if I shift down 2 and cosine, so let me see, 1, 2, 3, I think that should do it. If I shift down 2 and cosine normally starts here, right, It's going to go here, 1, 2, 3, and then go down to 2, 3, 4, 5. And so what's going to happen is my secant function is going to start right here where the y value is 1, and it's going to start down here where the y value is negative 5, which means my range is going to be everything above 1 and everything below negative 5. So how do I write that out? Well, I'll write that out as my range is going to be negative infinity, not including negative infinity because you can't. So negative infinity to negative 5, and including it, union, and then from 1 to regular infinity. So that's my range without doing too much, without having to graph what secant really looks like, because who really wants to do that? Let g of x be the graph below, and let f of x equals 1 over g of x. What is the equation of f of x? All right, well, this is g of x. So it looks to me that we kind of have ourselves a cosine function because it starts up here. The amplitude, that's 1, so that's a half. So the amplitude is a half, right? The period is 2 pi. And I see no vertical shifts and I see no horizontal shifts. So g of x is going to be half cosine x. They want me to find f of x, which is 1 over g of x. So f of x is going to be 1 over half of cosine x. Let's do this first. Let's multiply the top and the bottom by 2 to get rid of that half on the bottom, because that crosses out. That leaves me with 2 over cos x. When cos x is in the denominator, I could just move that up and make it secant x. And so that makes f of x equals 2 secant x. Fun, 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 funny, fun, fun. Verify the identity. Secant squared x minus cosecant squared x is the same as tangent squared x minus cotangent squared x. What you're doing here is you're basically starting with the left and you're doing some math trickery to see if you can end up with something on the right. So this is what I see here. I see a Pythagorean theorem identity right here, and I see a Pythagorean theorem identity right there. Secant squared x is the same exact thing as 1 plus tangent squared x. Minus cosecant squared x is the same thing as 1 plus cotangent squared x. Oh, how they look so similar to each other. Now, if I take this and distribute the negative, I now have 1 plus tangent squared x minus 1, how about that, minus cotangent squared x. The 1 and the negative 1 cancel each other out, and that leaves me with tangent squared x minus cotangent squared x, which is what I'm trying to find. So did I verify the identity? Sure did. A little check mark says I did it. Verify the identity. Cosecant squared x cosine squared x is the same as cosecant squared x minus 1. This is where I start out with the left side. I do a little math trickery to see if I can end up with something on the right side. Couple ways you could approach this. I mean, some people might look at cosecant squared x and do something with the 1 plus cotangent squared x, but I'm not going to do that because I don't think that's going to help me here. So instead what I'm going to do is I'm going to turn cosecant squared x into what its actual version is, 1 over sine squared x. Okay, that's going to be multiplied to cosine squared x. And now I have myself like a little fraction looking thing. Now what this fraction looking thing actually is cosine squared x over sine squared x. That is the same exact thing as cotangent squared x, Why? Because cos over sine is cotangent, so 2 coses over 2 sines is 2 cotangents, right? So now that I have that, I know that cotangent squared x is the same as cosecant squared x minus 1 because of the Pythagorean theorem identity, which is what I wanted to get all along. Look at that, I did it. Verify the identity sine 2x over cosine x equals 2 sine x. Basically, what I need to do is I need to take this guy, do a little bit of math magic, and see if I end up with 2 sine x. Well, this is what I know. I know that sine 2x is one of those double angle formula things. Sine 2x could be written out as 2 sine x cos x over cos x. And wouldn't you know it, something times something times something over something that repeats just crosses out, which leaves me with 2 sine x, which is what I'm trying to find. Look at that, easy peasy. Verify the identity 2 sine x cos x over cosecant squared x minus 1 equals tangent squared x sine 2x. What I need to do is I need to take the stuff on the left, do a little bit of math magic, and see if I end up with stuff on the right. Now, this is what I see right off the bat. I see what looks like the result of a double angle formula. And I see a double angle formula right there. And I look to be what results or what looks like a Pythagorean identity. And look, the other part of a Pythagorean theorem, kinda identity. So let's do both of those on the left side. I know 2 sine x cos x is the result of doing sine 2x because of the double angle identity. I know that cosecant squared x minus 1 is the same thing as cotangent squared x. Now, does that get me what I want? No, but what else do I see? Cotangent's in the denominator, which means if I move it upstairs and turn it into tangent, I get tangent squared x times sine 2x, which is what I'm trying to find. So did I verify? I sure did. Verify just like I am on Twitter. No, I'm not. And it's also called X. Find the exact value of cosine 17 pi over 12. Now, we know our unit circle, and there's nowhere on the unit circle that gives me 17 pi over 12. So this is what I can do. I can rewrite cosine as 2 angles being added together. So something like this, right? So what 2 numbers could I add together to get me the 17 that if I divide them by 12, I get some magic numbers? Well, let's try 9 pi. And let's try 8 pi. And what that does is that gets me cosine 3 pi over 4 plus 2 pi over 3. And now those on separate occasions are things that I can do. Now, why am I doing this? Well, I'm going to use basically what's called the angle addition identity for cosine. I'm sure I botched the name on that, but you get the idea. So this is me following this rule right here. Cosine alpha, named after me, plus beta, not named after me, is the same exact thing as cos alpha cos beta minus sine alpha sine beta. So if I follow these rules and pretend that you're alpha and pretend that you're beta, I'll be able to get exactly what I want using the unit circle and stuff like that. So I can rewrite this as cosine 3 pi over 4 times cosine 2 pi over 3 minus sine 3 pi over 4 sine 2 pi over 3. Now, these are all unit circle guys, so I have them memorized. I'm going to go through them kind of quickly. If you need help with these, go back and watch some other videos and get me some of that sweet YouTube money. Cosine 3 pi over 4 is negative root 2 over 2. Cosine 2 pi over 3 is negative a half. Minus sine of 3 pi over 4 is regular root 2 over 2.
sine 2 pi over 3 is regular root 3 over 2. Negative times a negative is a positive. Root 2 times 1 is root 2 over 4 minus root 2 times root 3 is root 6, and 2 times 2 is regular 4. Root 2 minus root 6, both of them over 4, is going to end up being, and let me put it over here where I have a little bit more space, root 2 minus root 6 over 4. I can't simplify that any further. Don't even try it. Don't even be like, they're evens. Nah, they're square roots. They're not even. So that's it. That's the cosine addition identity, trigonometry, postulate, theorem, axiom thing. Thank you for watching. I hope this helps.
Buckle up for this one. It's a doozy. Find the exact value of tangent 5 pi over 12. Obviously, we're not given on the unit circle 5 pi over 12, so I need to kind of rewrite this in a way where I use some of those numbers that seem to appear on a tangent circle, and I can either add or subtract them. Now, what I'm going to do is I can get to 5 pi by doing 2 pi and 3 pi over 12. Now, what that does is once I have those officially split up, I can write this out as tangent. 2 pi over 12 is pi over 6, so a unit circle number, plus 3 pi over 12 is pi over 4, another unit circle number. Now, you may have the sine, and hopefully you do, and the cosine addition properties memorized, but you probably don't have the tangent. So I'm going to go about this in probably the longest way possible, just in case you don't have tangent memorized. Tangent is the same as sine over cosine. So I can write this out as sine pi over 6 plus pi over 4 all over cosine pi over 6 plus pi over 4. Okay? And then I deal with each one individually, which is not going to be super pleasant. But you know what? That's kind of what I get for not having tangent memorized, because honestly, I don't have it memorized. So basically, when you add two sines, what you do is you do sine of the first, cos of the second, plus cos of the first, sine of the second. So sine of the first, cos of the second, plus cos of the first, sine of the second. Barely squeezed that in there. Barely squeezed it in. Cosine is, if you're adding them, is going to be cos cos minus sine sine. So cos of the first, so cos of pi over 6, cos of the second, so pi over 4, again, minus sine of the first, so sine pi over 6, sine of the second, pi over 4. Now, I'm assuming at this stage we feel okay with the unit circle, so I'm not going to spend a lot of time reminding ourselves how to find the sine of pi over 6. So, you know, we're just going to go right to it. Sine of pi over 6 is a half. Cosine of pi over 4 is root 2 over 2. Plus cosine of pi over 6 is root 3 over 2. And sine of pi over 4 is root 2 over 2. Cosine of pi over 6, which I already did, is root 3 over 2. Cosine of pi over 4, which I already did, is right here, root 2 over 2. Minus sine of pi over 6, which I did over here, is a half. Sine of pi over 4, which I did, is root 2 over 2. Okay, so this is where it's going to get fun. Root 2 times 1 is root 2. 2 times 2 is 4. Root 3 times root 2 is 6. 2 times 2 is 4. You're adding on top. All over. You're subtracting on the bottom. Let's get a different color, all these colors. Root 3 times root 2 is root 6. 2 times 2 is 4. And purple. 1 times root 2 is root 2. 2 times 2 is 4. So they combine nicely. Root 2 over 4 plus root 6 over 4 is root 2 plus root 6 over 4. Root 6 minus root 2 over 4. Now, since these are both over 4, I can multiply the top and the bottom by the reciprocal of the denominator, which I'm just going to kind of skip that step and go right to, actually, you know what, let me write it down here because I know what's going to happen next. Root 2 plus root 6 over root 6 minus root 2. Now, chances are you're going to have a teacher or a test or a problem where you're not allowed to have square roots on the bottom. So how do I eliminate a root minus a root? You do the conjugate, which is going to be multiplying the top and the bottom by that root plus the root. And what that does is that gives us difference of squares type problems. Now, upstairs, it doesn't give us difference of squares. It just, FOILs out. So if you were to put these in parentheses and put these in parentheses, you would FOIL things out. Root 2 times root 6 is root 12. I can simplify that. Root 2 times root 2 is 2. Root 6 times root 6 is 6. And root 6 times root 2 is root 12 again. Root 6 times root 6 is 6 plus root 12 minus root 12. So the root 12s go away. Root 2 times root 2 is 2, so that's going to be minus 2. All right, so that's 2 root 12. If I add the 2 root 12s together, plus 8. 6 minus 2 is 4. Still not done yet. Root 12 can be simplified to 2 root 3. So this becomes 4 root 3 plus 8 over 4. Now, still not done because I have a 4, an 8, and a 4. They're all divisible by 4. So last but not least, 4 root 3 divided by 4 is regular root 3, and 8 divided by 4 is 2. That is my final answer. So I told you, buckle up. Okay, hopefully you did. It's the law in many states, unless you're sitting in the back. All right, never mind. Like and subscribe. Simplify sine negative 6 theta, cos 4 theta, cosine negative 6 theta, sine 4 theta. Sine, cos plus cos sine is an awful lot like the addition formula for sine. In other words, if you see something that looks like this, I can just write this out as sine negative 6 theta plus 4 theta because of the formula. Combining these two is sine negative 2 theta. That's my guy, Dunzo. Not too bad. The terminal ray of an angle in standard position intersects the unit circle at the point with coordinates AB. The terminal ray of another angle in standard position intersects the circle at point CD. But if the measure of the second angle is double the measure, express the coordinates C and D in terms of A and B. So let's not draw an entire unit circle. Let's draw just a quarter of it. All right, let's call you A, B. And that's created by this radius with a terminal ray of theta. CD is going to be double that, so somewhere up here. CD is going to be double that, so somewhere up here. Perfect line. And that whole thing is going to be 2 theta. Okay? That's going to be 2 theta. So AB. If I'm thinking unit circle thoughts, usually that's x, y, and we say that x is cosine and y is sine. Same idea. Okay, A is going to be cos theta, and B is going to be sine theta. CD is going to be the same exact thing, but instead of theta, it's going to be cos 2 theta and sine 2 theta. Now what I have is I have double angle formulas, so let's turn these into what they're supposed to look like. Cosine's double angle formula is cos squared minus sine squared, so you become cos squared theta minus sine squared theta. And sine 2 theta is 2 sine theta cos theta. Now, how is this going to be me turning A and B into C's and D's? Well, C and D is this now. If I called A cos theta, then I can replace every cos theta with A. So CD is A squared minus, if I called B sine theta, then every sine theta is going to be B, so B squared. So 2 sine theta is 2B, or not, and cos theta is A. So CD can be rewritten as A squared minus B squared and 2AB or BA. It all depends on if you like ripped stomach, muscles, or sheep. Thanks for watching. Hope this helps. Solve the equation for 0 is less than or equal to theta, which is just less than 2 pi. All right, so I'm solving this guy with tan squareds and stuff like that. I have a tan squared on the left, a tan squared on the right. Why don't I add tan squared to both sides, set it equal to 0? I have a feeling we're going to have some kind of factoring stuff going on here. Okay, so this left side becomes 1 minus 1 tan squared theta. That's going to equal 0. Now, if we were to look at this as something like, this is almost like 1 minus x squared, and that's difference of squares, so just do something like this, you're thinking the exact right thoughts. This is 1 minus tangent squared. So why can't I write this as 1 plus regular tangent 1 minus regular tangent and set that equal to 0 and do the 0 product property? Well, I have news for you. I can and I will. So what you do with the 0 product property is you take each product, you set it equal to 0. So 1 plus tan theta equals 0. And if I subtract 1 from both sides, I have tan theta equals negative 1. Okay, I'll hold on to that. This guy, if I were to, let's do it this way, add tan theta to both sides, that gets me 1 equals tan theta. Well, let me write it out. Let me write out the whole thing first. Let me write out the whole thing first and be consistent. I should write this out as 1 minus tan theta equals 0. Let's add tan theta to both sides. There you have it. So in order to get theta all by itself, you inverse tan both sides. So theta is going to be the inverse tangent of negative 1. Also, theta is going to be the inverse tangent of regular 1. Now I'm focusing on unit circle stuff where I only care about numbers and thetas between 0 and 2 pi. So again, if you're not sure how to, like, what this means, the inverse tangent of negative 1 means on the unit circle, go back and watch a few videos from a few sections ago. But the inverse tangent of negative 1 is 3 pi over 4 because it means like a slope of negative 1. So theta is going to be 3 pi over 4. Now that's not the only one because the period of tangent is pi. So if I add pi over or to that, I also end up with 7 pi over 4. That is the inverse tangent of negative 1 between 0 and 2 pi. Similarly, the inverse tangent of 1 is basically asking me, what angle measures give me a slope of 1? Well, that's going to be regular pi over 4. And since the period of tangent is pi, I'm going to add pi to that and get 5 pi over 4. So I have 4 answers here, and those are my 4 answers based off of the way that I did it.
Solve the equation for everything in between 0 and 2 pi. I have 3 cosecant squared theta on the left, and I have 1 on the right and 2 cosecant squared theta on the right. So I'm thinking these two will combine somehow. So why don't I subtract 2 cosecant squared theta from both sides? Cosecant squared theta. And while I'm at it, why don't I subtract 1 from both sides too? So the right side becomes 0. 3 cosecant squareds minus 2 cosecant squareds is 1 cosecant squared theta, and then minus 1 equals 0. Now, if you're looking at this and thinking, wait a minute, something squared minus 1, which is also a square, can I make that difference of squares? Mm-hmm. And what that would look like is the square root of that plus the square root of that times the square root of that minus the square root of that. So cosecant squared, theta, plus 1, cosecant theta minus 1 equals 0. And now I have 0 product property. Okay, cosecant theta plus 1 equals 0. And if I subtract 1 from both sides, cosecant theta equals -1. I'll deal with that in a minute. Cosecant theta minus 1 equals 0. Add 1 to both sides. Cosecant theta equals 1. All right. Real talk. I don't like cosecant. I don't deal with cosecant. I'd rather view cosecant like this. So I'm going to rewrite it like this. I'm allowed to do that. 1 over sine theta equals -1, and 1 over sine theta equals regular 1. I'm allowed to do that because cosecant is the same as 1 over sine. Okay? And if I do that and kind of treat this like a proportion and do crisscross applesauce, I would have sine theta equals -1, because I would do these two multiplied together, these two multiplied together, and multiply both sides by negative. And I would have sine theta equals regular 1. If you inverse sine both sides, that allows theta to be all by itself. So if I inverse sine both sides, I now have theta equals the inverse sine of -1, and theta equals the inverse sine of +1. Okay. Theta equals the inverse sine of -1 is asking you, when is the y value equal to -1 on a unit circle? Well, only one spot, and that's at the bottom of the y-axis. And that happens at 3 pi over 2. So theta is going to be 3 pi over 2. Similarly, when is it 1? Well, that's when it's on the positive y-axis, and that's at regular pi over 2. And those are my only two answers for this guy. Okay, those are my only two answers for this guy, just them. And yeah, that solves my equation, and that also fits the constraints of between 0 and 2 pi. Tons of fun. Solve the equation for everything between 0 and 2 pi. I've got 2 root 3 cos theta sine theta minus cos theta equals 2 cos theta. All right, so looking at this, I have a sine and a cosine. I kind of am thinking I could probably factor stuff out if I just remove this guy from the right side. So why don't I remove cos, 2 of them, cos theta, from the right side? And you know what? That would combine nicely with u, won't it? So that leaves me 2 root 3 cos theta sine theta minus 3 cos theta equals 0. Now I have a cosine in common with both of these major terms. So if I just factor out a cosine theta, that leaves me with 2 root 3 sine theta minus 3. And that's going to equal 0. So a factor times a factor equals 0 means 0 product property. Starting out with the lovely one first, and I'll just write that here, cos theta equals 0. So if I inverse cosine both sides, theta will equal the inverse cosine of 0. Okay, that happens at 2 spots. At pi over 2, where the x value is 0, and at 3 pi over 2, where the x value is 0. And of course, that follows in the constraints of between 0 and 2 pi. Now, this other guy, I'm going to write up here where I have a little bit more space because I'm going to have to do a little bit more. 2 root 3 sine theta minus 3 equals 0. Step 1, add 3 to both sides. So 2 root 3 sine theta equals 3. Step 2, divide both sides by 2 root 3. Divide both sides by 2 root 3. And so that gets you sine theta equals 3 over 2 root 3. And you know that's no good because the square root's on the bottom. So if you multiply the top and the bottom by root 3 over root 3, okay, you become 3 root 3. 2 times root 3 is 2 times 3, which is 6. This guy simplifies that to a much friendlier looking number. Root 3 over 2. Now, when is sine theta root 3 over 2? Well, let's inverse sine it. Let's inverse sine it just to be proper. Well, I'm not going to show my work because I'm running out of space here. Theta is going to equal the inverse sine of root 3 over 2. And where you have a y value of a positive root 3 over 2, you have that at pi over 3 and 2 pi over 3. And that follows, of course, the constraints of everything in between 0 and 2 pi. So, those are my answers. Isn't that neat? Solve the equation for theta is in between 0 and 2 pi. So I'm given 3 sine theta plus 2 sine squared theta equals negative 1. Well, why don't I add 1 to both sides and set it equal to 0? By doing that, and maybe rewriting it in a clever way, I have 2 sine squared theta, because now I'm writing it in standard form because I have a feeling I know what's going to happen, plus 3 sine theta plus 1 equals 0. Now, make believe that sine is a. So I have 2a squared plus 3a plus 1. And if you're thinking, oh, that's something I can factor, you're thinking the right thoughts. But a is sine, so I have to treat it as such. So that factors out to 2 sine theta plus 1 times regular sine theta plus 1. And if you FOIL that out, you'll realize that I'm right. Trust me on this one. Now I have zero product properties. Set them each equal to 0. So 2 sine theta plus 1 equals 0. Subtract 1 from both sides. Divide 2 from both sides. And now sine theta equals negative a half. Okay, if I inverse sine both sides, and I'm running out of space, so I'm hoping that this shows up in the video. If I inverse sine both sides, I have theta equals the inverse sine of negative 1/2. Now, the inverse sine of negative a half is asking me where is the sine or the y value going to equal negative 1/2 on the unit circle? Well, that happens at 2 spots, 7 pi over 6 and 11 pi over 6. So that's answer number 1 based off of the left side of this zero product property problem. Now what I have is a slightly easier one where it's sine theta plus 1 equals 0. I subtract 1 from both sides, so sine theta equals negative 1. I inverse sine both sides, so theta is going to equal the inverse sine of negative 1. Now where is the y value negative 1 on the unit circle? Only one spot, and that's going to be on the negative y-axis where 3 pi over 2 exists. So yeah, that's it. That's 3.12. Lots of solving for trig stuff.
Rewrite the polar coordinate with a negative magnitude. Now, before I even consider this, let's take a look at what we have. This is a polar coordinate. This is not what we're used to, which is called a regular coordinate. This is not telling us to start at the origin, go right 7, and then up whatever gross number this is. No, this is polar. And the two numbers involved in a polar coordinate, the first number is the magnitude. That's how long we draw a line starting from the 0, 0, which is also called the pole in a polar coordinate system. This is the degrees that we go, just like we've been doing all year long or all AP Precalculus long, where we would start out counterclockwise from the positive y-axis, x-axis. So, graphing something like this, right? There's my direction, 11 pi over 6 is you spin it all the way around, so it's basically like that, and we have something that's 7 units long, and so my point would live right there. Okay, now, they want us to do a negative magnitude. Well, a negative magnitude, if I were to take this same exact guy and make this negative 7, what I would do is I would still spin it around to 11 pi over 6, but I would go in the complete opposite direction, that way 7 units. Okay, now what I need to do is if I'm going to make this negative 7, if negative 7 has me going in the exact opposite direction, that's a change of 180 degrees, or pi radians. So if I'm going to make this negative 7, then what I need to do is I need to spin this guy around in the exact opposite direction. So I'm going to either add, or in this case, subtract pi. Now, why not add pi? Well, if I add pi, it'll be more than 2 pi, and I want to keep it between 0 and 2 pi. So subtracting regular pi is going to make this look like negative 7. I'll change this pi to 6 pi over 6, and I end up with negative 7, 5 pi over 6. And so the way that I would graph this now, pretending that this guy is no longer there, let's erase you. The way that I would view this graphically is I would go counterclockwise from the positive x-axis to what appears to be 5 pi over 6. But since this is negative 7, I'm going to go in the exact opposite direction and graph the original guy that you see right here. And that's how it's done. Graph the polar coordinate 3 and then 3 pi over 4. Now, we're used to seeing what's called a rectangular coordinate, where when we see two numbers, we think, oh, well, let's go right 3 and then go up whatever 3 pi over 4 is. No. This is a polar coordinate. Polar coordinates are given to us where the first number is r. R is the magnitude. R is how far away we draw our coordinate from the 0, 0, or the pole axis. 3 pi over 4 is the degree that we go if we were to go counterclockwise starting from the positive x-axis. Basically what we've always done. So what I do is I start from 0 and I go to 3 pi over 4, which I don't have labeled, but I know 3 pi over 4 is this guy right here. And so this is the line that represents the angle 3 pi over 4. And then since 3 is the magnitude, I'm going to go 1, 2, 3 units away from 0, 0, the pole. Put a nice little dot right there, and that's it. That's my answer. That's how you graph a polar coordinate. Graph the polar coordinate negative 3, 23 pi over 12. Now, when you graph a polar coordinate, this is not the same as what we're used to, the rectangular coordinate. This is not telling us, let's go left 3 and then go up whatever the heck that number is. This first number is the magnitude. This is how long or how far away we're going to draw our dot from 0, 0, also known as the pole. This second number is the degree that we spin counterclockwise from the positive x-axis. Okay, like we've always done. Now, 23 pi over 12 is not visible, but it would be right here. Okay, it's literally that last spot before we hit 2 pi. Now, that's great and all. So I spin this around, I see 23 pi over 12, and I'm like, well, wait a minute. My magnitude is negative 3. That means I'm not going to go 1, 2, 3 towards 23 pi over 12. I'm going to go in the opposite direction. So 23 pi over 12 is this line, which in the opposite direction, spinning it around, is going to be this line. And I would go 1, 2, 3 spaces down this line, which represents 11 pi over 12. So the way you can view this is if you're going to have a negative magnitude, just add or subtract 1 pi to this number here and make that negative magnitude positive, and you get the same thing. So negative 3, 23 pi over 12, is the same as positive 3, 11 pi over 12, because 23 pi over 12 minus pi is that number right there. So there you have it. That's how you graph a negative magnitude polar coordinate. Fun, 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 fun. Convert the polar coordinates to rectangular coordinates. So this right here is polar coordinates. That 2 is your magnitude. That's how far away you're going to draw a dot from 0, 0. That 11 pi over 6 is going to be the angle that you use to place that dot. So a quick rough draft of this is if I were to have a regular polar coordinate plane, you would spin this guy around to 11 pi over 6, and then which is going to be right around here, and then you would count 2 spaces and you would end up with a dot like right there. I have to make that look rectangular. What does it mean to draw a dot on a rectangular plane that is 2 units away from 0, 0, but at an angle of 11 pi over 6? Well, the way you turn something that's polar into XY form is you allow x to equal r cosine theta. Now that should look familiar. When you first learned about unit circles where the radius isn't 1, you learned that x was r cos theta. Similarly, y is going to be r sine theta. And then what we do is we just kind of plug in what we know and do a little bit of math and take it from there. So let's take care of x completely first. This is going to be 2 cosine 11 pi over 6. 11 pi over 6. When you do the math, that becomes root 3 pi over 2. So x is going to be 2 cosine root 3 pi over 2, and that's because the dot is the third dot on a unit circle, blah, 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 blah. 2 root 3 over 2 allows the 2's to cancel out, and our x value is just going to be root 3, 1 point something. Our y value is going to be very, very, very similar, where it's going to be 2 sine 11 pi over 6, like so. Since that's the third dot on the thing and it's the y, it's going to become 1/2. So this is going to be y equals 2 sine. And you know what? Since this is in the fourth quadrant, y is going to be negative. So this is negative 1/2. And 2 times negative 1/2 is negative 1. So the rectangular coordinates for that guy right there is going to be root 3, so 1 point something, negative 1, which makes sense. If we were to go right 1 point something and down 1, that seems to associate with the polar coordinate that we drew up there. So that's how you do it. Same as it. It's very familiar looking stuff, so not overly complicated. Express the complex number 5 plus 5i in polar coordinates in the form r cos theta plus I r sine theta. So this is very similar to graphing like a normal point in polar coordinate form to rectangular form. It's just now I have i's attached. Now, if you've never seen a complex number graphed, it's very, 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 very similar to graphing a regular point. You have yourself your real axis, you have yourself your imaginary axis, and in this case, our real number is 5, so you would go right 5. Our imaginary number is 5i, so we would go up 5, and we'd end up with a dot that you get from going right and up 5. Now, I need to make that associate with something that is much more rectangular, okay, or much more polar, because this is rectangular. So this is what we do. If I want to find my r in both cases, you are going to label this a and b. R is going to be the square root of a squared plus b squared. Now, r represents the magnitude, the distance from 0, 0 to our dot. It would make sense that the distance from the magnitude to our dot is kind of done in a very Pythagorean theorem way, where you would kind of take this number squared plus that number squared equals like c squared, like the Pythagorean theorem. Well, this is basically the Pythagorean theorem. So if a is 5 and b is 5, we have the square root of 5 squared plus 5 squared, which is 25 plus 25, which is the square root of 50. And you know that 50 is 25 times 2, so you can rip out a 5 and you're left with 5 square root of 2. So that's my r. That's my r. What I need now is I need my theta. My theta represents this degree here. It would make sense that if I know that you are 5 and I know that you are 5, I'm going to use a trig function that deals with the adjacent and the opposite sides. That's tangent. So tangent theta is going to equal opposite over adjacent, or in this case, tangent theta, whatever that theta is going to equal b over a. So if tangent theta equals b over a, then theta equals the inverse tangent of b over a. So theta is the inverse tangent of 5 over 5, which is the inverse tangent of 1. And the inverse tangent of 1 is a perfect slope of positive 1, which is going to be pi over 4. So theta is pi over 4. Now that I know what r is and now that I know what theta is, I can say that my number in polar coordinate form is going to be 5 root 2 cos theta, which is pi over 4, plus 5 root 2, let me sneak the I right in there, sine pi over 4. Okay, so not the prettiest looking thing in the world, but it makes sense that that's what we get by using the information that we were given. Fun stuff. Graph the polar coordinate 4 root 2 7 pi over 4. Now, this is a polar coordinate, and polar coordinates are in the form r theta. Now, when I were to graph this, like, I'm going to make a rough draft over here just so we can kind of compare the two. Whenever you're looking at a polar coordinate, your magnitude is how far away from 0, 0 am I going to draw my dot. 4 root 2 is like 5 point something or 6 point something. 7 pi over 4 is the direction that I go if I were to start out at the positive x-axis and spin it counterclockwise. 7 pi over 4 is this direction right here. So me drawing a dot like 5 or 6 units away in the 7 pi over 4 direction is going to be somewhere down there. So I know my answer is going to be somewhere down here. Now I need to find it out. Rectangular coordinates are x, y coordinates. And when you first learn about unit circle, especially unit circle where the radius is not 1, you learn that x is going to equal r cos theta, and y is going to equal r sine theta. So now it's a matter of taking this information that you already know, plugging it into these two equations, and using unit circle information to figure out the rest. So x is going to equal r, which is 4 root 2, cos theta, which is 7 pi over 4. Okay, cos of 7 pi over 4 is root 2 over 2. So root 2 over 2, x is going to equal that. Okay, 4 over 2 is 2, and root 2 times root 2 is also 2, so x is going to equal 4. Okay, regular old 4, easy peasy lemon squeezy. I'm going to do the same exact thing with the same exact numbers, but now it's a sine. So 4 root 2 sine 7 pi over 4. The sine of 7 pi over 4 is negative root 2 over 2. So y is going to equal 4 times root 2 times negative root 2 over 2. 4 over 2 is 2, and 2 times root 2 times root 2 is the same as 2 times 2, which last time I checked is 4. So my rectangular coordinate is going to be the point 4, negative 4. So 4, negative 4 is going to be my dot. So my little prediction that I drew up here ended up being pretty accurate. Big surprise. I kind of knew that was going to happen. But what I didn't know is that the numbers would be so nice. But before I end the video, here's why the numbers are so nice. This is a perfect diagonal, which means if you were to cut, if you were to cut this guy into a perfect triangle, this would be a 45, 45, 90 triangle. You would be 4, which means you would be 4 root 2. So it kind of all ties back to everything that we've learned back in geometry and all that fun stuff. It never seems to go away. Convert the rectangular coordinate here into polar coordinate. So this is a rectangular coordinate, and I need to make it look like this. Now, what we do when we're dealing with, rectangular coordinates is I know that this is going to be some point in the third quadrant, right? It's going to be some point down here somewhere, don't know exactly where, but it's going to live down there. What I need to figure out is if this is my x value, right here, that point's going to be over here, and it's going to be x units away. That's going to be y units down there, and my job is to find some type of theta given all this information right here. Well, wait a minute. If I need to find how far away that dot is from the origin, and I know that this is kind of like a right triangle, and I know like the leg of a right triangle and the other leg of a right triangle, and I need to find the hypotenuse of a right triangle, why don't I just use Pythagorean theorem? So the way we can find r is we could just take the square root of x squared plus y squared, which is our AP Precalc version of the Pythagorean theorem, where it's usually a squared plus b squared equals c squared. We just have different letters, and then I'm taking the square root right away. So r, and this is not going to be the easiest math in the world, but we'll be all right. R is going to be negative 5 times the square root of 3 over 2 squared plus the negative 5 over 2 squared in parentheses, gross. So r is going to be big square root. 5 times 5 is 23. Root 3 times root 3 is 3. So 25, not 23, stupid, times 3 is 75. 2 times 2 is 4. Negative times a negative is a positive. 5 times 5 is 25. 2 times 2 is 4. 75 plus 25 is 100. 100 over 4 is 25. So r is the square root of 25, which means r is 5. Beautiful number. Beautiful, beautiful, beautiful. Now, the next thing I need to figure out is that angle right there. Now, that angle right there is basically found by me taking this opposite side right here and that adjacent side and me trying to find that angle. Well, how can I find the angle using an opposite and adjacent side? Tangent. Tangent would do that. So tangent of my angle would equal y over x, opposite over adjacent, which means the inverse tangent of my angle, which was what? I don't know. I do know. The inverse tangent of my x or y over x is going to give me my theta. So the theta is going to be the inverse tangent of y over x. Okay. So theta is going to be the inverse tangent of negative 5 over 2 all over negative 5 root 3 over 2. Root 3 over 2. So let's multiply the top and the bottom. Let's multiply the top and the bottom by 2 over 5 root 3. And since these become positive, I could just get rid of that. 2 over 5 root 3 so that these guys cancel out. So theta is going to equal the inverse tangent of 2's cancel out. 5's cancel out. 1 over root 3. Well, that's still no good. So let's multiply the top and the bottom by root 3 over root 3. And so theta is going to be the inverse tangent of root 3 over root 3 times root 3 is regular 3. The inverse tangent of root 3 over 3 is pi over 6. So this point in polar coordinate form is going to be 5 pi over 6. But that doesn't seem right because it's down here. So what I need to do is I need to add pi so that it spins it into the third quadrant. So if I put 6 pi over 6, that gets me 7 pi over 6. So my final answer is going to be 7 pi over 6. You kind of have to be careful because I think a lot of people would answer this as 5 pi over 6, but you have to keep in mind the inverse tangent of any number is going to have two possible answers because the period of tangent is pi. So you kind of have to have that picture in your mind that when I'm done, if I get something that appears in the first quadrant like this did, I have to add pi to it so I get the right answer that I need. And that's the answer that I need. Or another option is you can keep this as pi over 6 and make that negative 5 so that it kind of spins it in the opposite direction. Either way, we have to change one of them, and so that's the way that I did it. Like I said, the other option is negative 5 pi over 6. So, pick your poison. Find the distance between the polar coordinates. All right, so these are two polar coordinates. I'm going to kind of draw a rough draft of what's going on. Now, fortunately, both of these have the same magnitude. So if I were to draw like a unit circle with radius 2, both of these would fall on the same circle. Now, 2 pi over 3 is going to live like somewhere around here. Okay, so that's dot number 1. Okay, now that gives me an angle of pi over 3 right there. This is going to be 11 pi over 6. Now, I'm not going to write 11 pi over 6 here because that is not going to be what this angle is. 11 pi over 6 is pi over 6 radians away from the positive x-axis. So what I need to do is I need to find the distance between these 2 points right here. So redrawing this picture out, this is what I know. I know that you're 2. I know that you're 2. I know that this angle is going to be pi over 3 plus pi over 6. So 2 pi over 6, pi over 3, plus pi over 6 is 3 pi over 6, or pi over 2. Okay, so you are going to be 2 pi over 2 and 2. Now, I'm going to pretend that I don't know that this is a 90-degree angle because I want to treat this as if it's any old radian that I can handle. So if you have a side angle side situation where you're trying to find the opposite side, we use what's called the law of cosines. The law of cosine says that if you have a leg, another leg, and a big angle in between that leg, I can take the hypotenuse that I have, square it. That's going to equal a squared plus b squared equals 2ab cos big C. That's the law of cosines. And what this does is this gives me all of this information, and I'll be able to find little c, which is what I'm trying to find. So little c squared equals 2 squared plus 2 squared. That's supposed to be minus, and I don't know why I wrote out an equal sign, minus 2 little a, little b, cos big C, which is pi over 2. C squared is 4 plus 4 minus 8 times cos 2 or pi over 2, which is 0. So you go away. C squared is 8. Square root both sides, And you get the square root of 8, which is the square root of 4 times 2, which is 2 root 2. So C, regular C, is 2 root 2. Regular C is 2 root 2. And that's what I'm trying to find. I'm trying to find the distance between these 2 points. So I found it. And that distance is 2 root 2. Now, if we were to just go back here in the first place, I would have realized that, well, wait a minute, you're 90 degrees, which means you're 45 and you're 45. How do I know that? Well, these two are the same. So this is a 45-45 triangle, 45-45-90 triangle, which means that these two guys just make you 2 root 2. But I did law of cosines anyway because it's fun. Sketch a graph on a rectangular plane to help draw the polar graph for r equals 3 sine theta. Now, whenever I graph a polar graph for sine theta or cos theta, it has a very, very, very specific look as long as it's just sine theta or just cos theta. The number in front of it just makes that picture bigger. That's all it does. So let's kind of draw out what it's asking us to draw out. The trig version of 3 sine theta. Now, I know that 3 sine theta goes up to 3, bottoms out at -3. I know that magic happens at pi, then it repeats itself at 2 pi. It goes through stuff at pi over 2, and 3 pi over 2, yada, yada, yada. So if I were to draw this, it starts out here. At pi over 2, it peaks out at 3. At pi, it hits the x-axis again. At 3 pi over 2, it hits -3. And at 2 pi, it repeats. So, let's just draw a rough draft of what this looks like. Okay, knowing very well that I am not an artist. Those of you who've watched my videos know this. But this will help us kind of figure out what we have. Now, let's draw the dots that we have so far. Okay, this is the polar coordinate 0, 0. Okay, so basically, if I look at it this way, my y-axis is basically my r. Okay, and this is basically my theta. So this is the point 0, 0. This right here is the point 3 pi over 2. So I go to pi over 2, I draw a dot at 1, 2, 3, right there. Okay, at pi, I have 0 again. So if I were to go over to pi, I put a dot at 0 again. So it looks like, I just kind of hit that again. At 3 pi over 2, which is u, I'm at -3. So 3 pi over 2, I'm at regular 1, 2, 3, but spin it in the opposite direction, and I'm covering that dot again. So right now, and of course 2 pi is the same as 0. That's where it repeats. So, 2 pi is 0, the same thing. There's a dot. So really, I only have 2 dots. So drawing this graph, I'm kind of out of luck. So let's kind of find some in-between areas. Okay, so if I were to put a little mark here, 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 and here, that kind of gives me those in-between areas. Like at, pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4. I could put more dots there. It looks like at pi over 4, I'm at like the 2-ish range. So even though I can't see pi over 4, I'll write it out. At pi over 4, I'm at the 2-ish range, give or take. At 3 pi over 4, I'm also at the 2-ish range because this is sinusoidal and whatever it does over here, it kind of has symmetry. So I'm at the 2-ish range there. At 5 pi over 4, which would be u, at 5 pi over 4, I'm at like the -2-ish range, which means I'd go here, but in the opposite direction, which means that dot just repeats itself. So if this is going to be 7 pi over 4, and if I were to go 7 pi over 4, which seems to be in the -2-ish range, the same exact thing happens. So what's happening here is as I start out at, so I kind of see what's happening. It's circling around. So as I start at 0, 0, and as theta increases, I get further away from the 0, 0, from the pole, until I hit 3, and then I get closer to the pole as I approach pi. So starting out at 0, 0 and spinning around this way, I can kind of put like these dots around here, and that kind of gives me an idea. Okay. And, again, as I'm going from 0 to pi, I slowly go from 3 and then back to 0. So from 0 to pi, I go from 3 and back to 0. Now, from pi to 2 pi, I do the same thing, but negative. So as I go from pi to 2 pi, I go like this circle, but in the negative area. So when all is said and done, what I do is I loop around and make a circle twice. But you don't see it twice. All you see is just a nice, perfectly round circle. So whenever we have 3 sine theta, 4 cos theta, 8 sine theta, negative 20 sine theta, whatever, if it's sine theta with no frequency in front of it, we're going to have a circle. And the size of that circle is going to be based on a 3. So this goes out to 3 and it makes a sine. Cosine is going to be over here. Negative cosine is going to be over here. And negative sine is going to be over there. So a lot of problems that you would see on the AP Precalculus exam might be like, look at this guy, pick the picture that works. And you could make a trig graph and do the long way, or you could just memorize the fact that if it gives you a circle, if it gives you something that looks like this, or something that looks like this, or something that looks different, you're going to pick the circle because sine theta or cos theta, when drawn on a on a polar plane, gets you a circle. Isn't that neat? Make a table to help draw the polar graph for r equals 4 cos 3 theta. All right, so we're making a table. This is going to be a doozy, or maybe I should say a daisy. Oh, that pun probably won't make sense for about 10 minutes. But if I remember, I'll bring that pun back and remind you why that would be so funny. So I'm going to make a table. In a previous example, what I did is I graphed the polar graph by making the actual graph of the sine or cosine function, whatever it was. Now, this is r cos 3 theta. So it's 4 cos 3 theta. So it's going to peak out at 4. And what's going to happen, since that's a 3, that means that's going to be how many times it repeats itself until it hits 2 pi. So I start up here, bottoms out, repeat, bottoms out, repeat, bottoms out, repeat at 2 pi. So as I make this table, I should expect things to repeat. Now, in the previous video, it was, I believe, some number sine theta, and when I graphed that, it was a circle. This is going to take on a different shape because of the number being multiplied to theta. And these shapes will be specific depending on the number multiplied to it. We'll talk about that at the end too. But let's tarry no further. Let's pick all of the angles that I see until I run out of space, because like I said, what's going to happen soon is things are going to start repeating. So I'll pick 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 3, pi, and then we'll see what happens if I need to make any more. All right, I'm going to plug in that theta into 4 cos 3 theta, and that'll give me an r value. All right, so if I do 4 cos 3 times 0, that's going to be 4 cos 0. We'll deal with that when we have to deal with that. 4 cos 3 times theta is going to be 4 cos 3 times pi over 6. 3 pi over 6 is pi over 2. I'll deal with that. 4 cos 3 pi over 3 is pi. 4 cos 3 pi over 2 is 3 pi over 2. 4 cos 3 times 2 pi over 3 is 6 pi over 3, which is 2 pi. Now, wait a minute. 2 pi is the same as 0. Oh, I wonder if this is where things start to repeat. I guess we'll find out. 4 cos 5 times 3 is 15. So 15 pi over 3 is 5 pi over 2. Well, hold on. That's beyond 2 pi. So this is just going to be pi over 2 if I were to subtract. So now we definitely see what's going on. That's the same as pi over 2. This next one is going to be the same as pi, because it would be 3 pi minus pi. So now we're repeating. All right, so let's do the math. Cos 0 is 1. 4 times 1 is 4. Cos pi over 2 is 0. So 4 times 0 is 0. Cos pi is negative 1. 4 times negative 1 is negative 4. Cos 3 pi over 2 is also 0. So 4 times 0 is 0. And now we repeat. So you become 4, you become 0, you become negative 4, and so on and so forth. So let's graph the points that we have right now. Okay, at 0, at angle 0, I go out to 4. At angle pi over 6, I stay at 0. At pi over 3, I go out to negative 4. Oh, I'm going the wrong way. So pi over 3 is going to be over here. 1, 2, 3, 4. Ooh, careful, careful, tricky, tricky. At pi over 2, I'm at 0. At 2 pi over 3, I'm at 1, 2, 3, 4. At 5 pi over 6, I'm at 0. 5 pi over 6. At pi, I'm at 0. At, well, hold on. So basically, if I'm repeating myself, right, this is going to just be like, all right, so what was pi? Pi, again, was negative 4. So you would be 0, you would be 4, you would be 0, you would be negative 4, you would be 0, 4. Repeat. So you're 0. You're 4, so I'm repeating my dot. You're 0. You're negative 4, so backwards 4, repeating my dot. All right, so basically, those are the dots that I have. Those are the dots that I see. A lot of them are just repeating. Okay, no big deal. Now what I need to do is start connecting these things. Okay, I need to start connecting these things. Since what I'm doing is when I'm starting out at 4, as I move towards pi over 6, I'm moving towards 0. So as I move towards pi over 6, I'm heading towards 0, so that happens. As I move towards pi over 3, I'm heading towards negative 4, so that's going to happen. As I'm moving towards pi over 2, I'm heading to 0, so that's going to happen. As I'm moving towards 2 pi over 3, I'm heading to 4, so that's going to happen. As I move towards 5 pi over 6, I'm heading to 0, so that's going to happen. And as I move towards regular pi, I head to negative 4, so that's going to happen. And then I repeat, and then I repeat, and then I repeat. Again, I'm at 0, and then this goes to 4. So there's no need for me to draw the same exact outline again because of repetition. So I repeat, okay? Now, what we have here is called a rose, which is what makes the daisy joke so funny. I'll pause for laughter. Okay. Now, fun fact, whenever you have number cos 3 theta, okay, or sine 3 theta for that matter. If you have sine or cosine 3 theta or 5 theta or whatever, if that number is odd, you get a rose with, if it's odd, if n is odd, you get a rose with n petals. So if you see a problem like this on a test and it's for cos 5 theta, you can expect a rose with 5 petals. If it was sine, it would start out at a different spot. It would just kind of shift over a little bit. almost as if this was a fan moving counterclockwise just a little bit. Now, what if this was something like 4 cos even petals? If n is even, what's actually going to happen is you're going to get double the amount of petals and things a lot more symmetrical. So it would be 2n petals. Okay, so if this was 4 cos 4 theta, you can expect a picture where it's 1, 2, 3, 4, 5, 6, 7, 8 total petals. So, yeah. But this is the typical rose problem. We really rose to the occasion on that one. Oh, like and subscribe. Sketch a graph on a rectangular plane to help draw the polar graph for r equals 3 sine theta. All right, so let's take this, and in a previous video I made a table. I'm not going to make a table. I'm just going to make a regular old trig graph based off of this information. Now, there's 2 things that I notice. There's a 1, which translates everything up 1. The amplitude is 3. So knowing how to graph trig functions, I know this is going to start out at 0, 1 because of that translation, and it's going to peak 3 units higher at 4 and bottom out 3 units lower at -2. So those are my key numbers, 1, 4, and -2. This is sine theta, and sine theta has a period of 2 pi, which means magic happens at regular pi and everything in between and everything in between. So let's start right here. I'm going to peak out at 4. I'm going to level out at pi where it's at 1. I'm going to bottom out at -2 and then repeat the process at 1. Okay, so let's draw a very, very, very basic curve like that, like so. Boy, did I blow it there. You get the idea. Now, let's graph some of the points that we can see. Okay, when theta is 0, I'm at 1. When theta is pi over 2, I'm at 1, 2, 3, 4. When theta is pi, I'm at 1 again. So this one right here. And when theta is 3 pi over 2, 3 pi over 2, I'm at -2. So +2 would be right here, but -2 would be right there. Now let's look at some in-betweeners, okay? And I'll mark them with the greens. I'll mark them with green. These are my in-betweener areas, okay? So in between 0 and pi over 2, maybe I'm at like 3-ish or something like that. 3-ish or something like that, give or take. Maybe a little bit more, so 3 point something-ish. I can actually do the math, but, who wants to do that? This is going to be the same 3.1-ish, 3-ish. So I'll put you here, okay? Here, maybe you're at like a -1. So -1 would be like maybe somewhere around here. And here you're also maybe at that same -1. So maybe there. All right, let's draw this out. I started out at 1. Okay, I started out at 0, 1. And I'm heading towards 2 pi, hitting that green dot along the way. So it's going to create like this circular thing that looks like that. Okay, as I go from pi over 2 to pi, I'm just making that circular thing going back to 1. Okay, as I go, and this is where it gets weird, as I go from pi to 3 pi over 2, I'm now hitting negative area going through that dot right there. And as I go from 3 pi over 2, I hit that dot right there and start at the very beginning, which is a very good place to start. So I have this weird shape thing, and I'm going to try to sketch it a little bit to make it look prettier. I have this weird shape thing where it kind of curls in. Now, why does it do that? Well, if I have what appears to be a vertical shift, I have a shape that in France is called a limaçon. I think it's spelled like that. Maybe with an A. Limaçon. Ha ha ha. We Americans, though, can't speak French, or at least I can't speak French. So a lot of people would call this a cardioid. And if you're like, cardioid? Cardioid. Oh boy. I can't spell in English or French. Now, if you're like cardioid, is there another I there? Oh, well, perfect. I think. I don't know. Who cares? This is a math class. I'm pretty sure that's how you spell cardioid. If you're thinking cardioid, well, that kind of sounds like a heart. It kind of is. As these numbers get bigger, you have like a bigger loop-looking thing. But if that number was like, kind of small or something like that, or if these numbers were smaller, you get what's called like a dimpled cardioid, which looks more like a heart. So maybe we would get something that looked like that. So that's more heart-shaped. But, the French people like to call it limaçon. Oui, oui. If you are French, I really apologize. Write a polar equation using the graph below. This is what I'm looking at. And what this looks like is a rose. Now, I did a video a couple problems ago where I had a rose. And the equation looks something like R equals some amplitude cos some number times theta. What we learned is when I had an odd number in front of theta, I had that many petals. I have 1, 2, 3, 4, 5, 6, 7, 8 petals. This is an even number. So when I had an even number, I had 2 times that many petals. This has 8 petals. So if I were to take a number and multiply it to 2 to get 8, that means my n would be 4. So this is going to be 4 theta. Okay. Now, fun fact here. I said cosine. Sine is also an option. If you're wondering, is this sine or is this cosine, and how do I figure it out? Well, if this was a cosine, cosine would always start out on the x-axis. This doesn't start out on the x-axis. This starts somewhere up here, which means this isn't cosine. This is sine. Tricky, 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 tricky. Now, I have to find the amplitude. That's the easy part. The amplitude is the maximum value that these petals stretch out to. These all stretch out to 3, which means the number in front of sine is also going to be 3. So the equation for this polar graph here is going to be r equals 3 sine 4 theta. Isn't that nice? Trace the parts on the graph that correspond to the interval pi over 2 and pi. All right, so here's my picture. I have myself a rose. I can see why this is 3 cos 4 theta because there's 8 petals. I can see why it's 3. It goes out to 3. What I need to focus on is which part of this graph exists between pi over 2 and pi. So this is what I'm going to do. This is how I'm going to view it. I'm going to, over here, graph what 3 cos 4 pi theta looks like. The 3 means it goes out to 3. 1, 2, 3. 1, 2, negative 3. So that happens. And I'm not going to make the prettiest looking picture ever. I'm going to be somewhat accurate. That 4 is my frequency. That tells me how many times I'm going to cycle before I hit 2 pi. All right. This cycles 4 times before 2 pi, which means if this is a cosine, it starts up here and then repeats and then repeats and then repeats and then repeats again. So that means if it's going to repeat 4 times before 2 pi, here are 4 intervals. Well, I know these numbers already. Your pi over 2, and your pi, and your 3 pi over 2. So my picture is going to start at 3, bottom out at negative 3, repeat. I know that looks awful. Repeat. That looks better. Okay, repeat and repeat. Now, what we care about is all the fun stuff happening in between pi over 2 and pi because of that. So at pi over 2, I have the value 3. So what I'm going to do is I'm going to go where pi over 2 is, here you is, and I'm going to go to 3. I'm going to label that right there, okay? As I go towards pi, I go towards 0 and then come back up and go towards 3 again. Okay, so at pi, I'm at 3 again, so I end here. So me drawing this, me tracing this, is going to have me going down to 0, hitting negative land, and then coming back to 3. So if I'm going down to 0, keep in mind, you're always going counterclockwise, so you're going this way. And as I go this way, I'm going down to 0. So this is me. Let me get a better pen. This is me tracing, so go down to 0. I'm going to continue following the pattern like so until I hit 3. So basically the picture that I get looks like that, okay, if I knew how to draw a little bit better. That guy right there. Okay, so that's me tracing from pi over 2 to pi. Isn't that pretty? Plot the point in the complex plane. I'm giving you a complex polar coordinate given to you in the form 3 cos stuff plus I sine stuff. Sometimes you're used to seeing it as r cos theta plus I r sine theta, but this is another way of writing it out. Well, this is how you graph these guys. 3 is your magnitude. That's the distance from 0, 0 to the point that you're going to draw out. There's my theta, and we treat that theta the way we've always treated theta. You start at the positive x-axis and you go your way counterclockwise. Now we are going to 7 pi over 6, and our magnitude is 3. So all we do is just draw a dot at what? 1, 2, 3 at 7 pi over 6. So that's it. Find the absolute value of this weird complex polar coordinate here. Absolute value is just fancy word for distance. The distance between 0, also known as the pole, and the dot that you would draw out. Well, the distance is going to be the magnitude. So the absolute value, the distance is 3. All right, thanks for watching. Have a good day. Consider the polar function r theta equals 2 plus 3 cos theta for everything in between 0 and 2 pi. At which angle does the function attain its maximum value? I'm not going to draw the polar coordinate of this. I'm going to just draw the regular old trig version of it. It's a cos theta. It goes up 2, peaks out 1, 2, 3 more because that's the amplitude, which means it bottoms out at -1. So it literally starts at 0, 5, and then repeats its process at 2 pi. All right, so without doing too much, I know this is going to look like this. So it begins at its maximum and ends at its maximum. Okay, and we're including both the beginning and the end if we want to, so 0 or 2 pi is an option. 0 is not an option, but there you are, 2 pi, so let's go with u. So remember, when I were to graph this, or if I were to graph this on a coordinate plane, it'll have some circular shape. And whatever that circular shape is, it's going to start and end furthest away from the pole. And that's what we're doing. Find the limit as theta approaches infinity of the polar equation r of theta equals theta to the 4th plus 5 over theta to the 10th minus 10. Now, before you start freaking out and begin wondering how the heck you're going to graph this thing, don't worry about graphing it. The way you treat a polar equation as the limit approaches infinity is the way you would treat a normal old equation with x's and stuff like that. As theta approaches infinity, I only care about the leading terms. So theta to the fourth over theta to the 10th. That simplifies to 1 over theta to the sixth. The limit as theta approaches infinity, where my degree in the numerator is higher, is always going to equal 0 no matter what. So that's not going to change just because this is a weird looking polar shape that is going to spin inward and eventually hit 0, which is what's going to happen here. Find the average rate of change of the polar coordinate or the polar equation. Find the average rate of change of the polar equation r of theta equals 2 cos 4 theta plus 1 on this interval pi over 8 to pi over 2. All right, so we know that the average rate of change is going to look like this. R of B minus R of A over B minus A. We know this from Unit 1. That would be my A. That would be my B. So what I need to do is I need to find R of pi over 2 and then find R of pi over 8. R of pi over 2 is going to be 2 cos 4 times pi over 2. Simplify that in a minute, plus 1. 2 cos 4 times pi over 2 is going to be 2 pi. So 2 cos 2 pi plus 1. The cosine of 2 pi is 1. So 2 times 1 plus 1 is 3. So this guy is going to end up being the number 3, no big deal. To find R of A, I'm going to do R of pi over 8. So the same idea, 2 times cosine 4 times pi over 8, close it, plus 1. That becomes 2 times cosine. 4 over 8 is a half, so a pi times a half is pi over 2 plus 1. Cosine of pi over 2 is 0. So that's nice. So this becomes 0 plus 1, which is 1. So now I have R of B, which is 3, minus R of pi over 8, which is 1, over B minus A, which is going to be, that's going to be the gross part, pi over 2 minus pi over 8. So that's going to be the worst part. 3 minus 2, not so bad. I'll turn u into 4 pi over 8 so I can subtract these two fractions. So 2 over 3 pi over 8. Let's multiply the top and the bottom by 8 over 3 pi. Multiply the top and the bottom by 8 over 3 pi. And at the end of the day, I end up with 16 over 3 pi. That's my guy. Fun stuff. All right, so in order to graph this crazy looking polar function, the first thing I need to do is go to mode and make sure my function is set to polar. When you do that and you click y equals, you'll notice that it's r's now. So we can start typing away. 2 minus 2 sine theta. And if you're like, don't you mean x? Nope, when you're in polar and you hit the x button, it actually gives you theta. Isn't that nice? So let's close that, plus sine theta again, close that. Let's open up a parentheses and do the square root of the absolute value of cosine. So math num gets us our absolute value. Okay, we're going to put cosine theta right in there, close the parentheses, hit right a bunch of times till you're definitely out of that square root, and now we can close the parentheses. The parentheses, not really too necessary. Let's divide by sine theta. Did I put two thetas? I think I did. Sine theta, close the parentheses, plus 1.4, close the parentheses. Now that should do it. Let's make sure that my mode is set to radians. It is. If I hit graph, that's what I get. Now that I could zoom a little bit. So let's zoom in and see what I have. Okay, let's move down so it centers things nicely when I hit zoom in. And let's see what I have. It's a heart. Aw, I made you guys a heart. You know why? Because this is the last problem of my random AP Precalculus example problems that I stole from the internet. And I love you guys for watching my videos. So this is me showing my affection the only way I know how. Math. Thanks for watching. Love you. Bye.